As you learned in the previous course, Java is used heavily in most daily interactions with computers, smartphones, and other internet-connected devices. When you interact with these devices, Java runs in the background, providing instructions that tell the devices what you want them to do through Object-Oriented Programming, or OOP. A good example is when you select Thumbs Up on a social media post, and the thumb emoji appears on screen. It's Java that bridges the gap between these two actions. But how can you program with Java to execute actions like this? In this course, you'll be introduced to Java programming concepts and techniques and learn how to use them to develop exciting applications. By the end of this course, you'll be able to organize and reuse code effectively to access it quickly when needed instead of creating it repeatedly. Apply object-oriented programming concepts within Java to design modular and scalable code that can adapt to your programming needs. And handle errors and exceptions in Java to create robust applications that won't run into performance issues, ensuring a smooth user experience. Let's take a few minutes to explore what awaits you. Before programming with Java, you must understand basic concepts like interfaces, abstract classes, and methods. A strong knowledge of these concepts will ensure you can manipulate objects to achieve your goals. You'll start developing your Java expertise by exploring concrete and abstract methods and learning how to create and use abstract classes. By mastering these basic concepts, you'll be ready to tackle all kinds of great Java projects. Designing a Java program also requires knowledge of building classes and organizing them into hierarchies, skills that you develop in this lesson and practice in a lab setting. Organizing your code using classes ensures you can quickly understand and amend it without issue. The final stage in mastering the basics of OOP is resolving a common problem in Java programming known as multiple inheritance, which you'll explore later in this course. Resolving this issue involves recalling your knowledge of interfaces alongside solutions like abstract classes. Having a good foundation in the basics of Java programming is a great start. But what happens when your programming doesn't work as intended because of errors? This is when you'll need to engage in defensive programming or error handling, the next stage of your Java education. Module 2 explores techniques for managing errors in Java programs. You learn to identify basic Java programming errors like checked and unchecked exceptions. Another skill you develop in this module is catching and handling different exceptions using try-catch blocks. Finally, a great Java developer protects their code using preventative measures such as avoiding, handling, and throwing catch-all, checked, and unchecked exceptions. Once you've developed these integral skills, you demonstrate them by applying error handling techniques and defensive programming strategies in a lab. Having completed modules 1 and 2, you'll be adept at the basics of Java programming and producing robust code free of errors. However, Java programming involves working with lots of different types of files. So how do you manage these files effectively? Module 3 explores these skills by reviewing processes for executing file handling operations in Java. Gain experience in these skills, then read from and write to files by exploring code examples that you can test for yourself. As part of the next stage in your file handling education, you work with input and output streams and handle character encoding and binary file. You'll then put your new file handling skills to use by writing different file types in the lab. The module concludes with common file I/O operations every great Java developer needs to know. These include creating, deleting, renaming, and copying files using directories. It also covers the serialization and deserialization processes. You'll show mastery of these techniques by managing sample files in a lab exercise. Finally, you test your newfound skills with a practical project. You'll integrate everything you've learned in this course to upgrade the Zoo program you built in the previous course to incorporate file I/O operations and serialize the application's state. Having completed this course, you will be able to program all kinds of incredible Java applications while ensuring your code is well organized, efficient, and error-free. Abstraction is everywhere. probably without you even realizing it. Take a social media messaging app, for example. Do you understand how it sends or forwards messages? Most probably not, unless you are a programmer. As an end user, you are unaware of all the technical details behind the app's functions. These details are hidden, allowing you to focus solely on messaging your friends without worrying about the underlying complexities. This hiding of details is what we call abstraction. In this video, you'll learn about abstraction, discover how abstract classes work, and explore how they use concrete and abstract methods so that you can hide the technical details of applications to ensure smooth experiences for your end users. Imagine a social media startup has hired you to develop the following buttons for their brand new messaging application: send message, like message, and forward message. This is a great opportunity to use abstraction, but it sounds challenging. Where do you even begin? The best place to start is by developing an understanding of abstract classes. An abstract class in Java is a class that cannot be instantiated. Such a class is declared with the abstract keyword. You can use the abstract keyword to declare an abstract button class to create the buttons for your app. This is followed by a pair of curly braces in which you insert the class body. The abstract class can have instance variables and methods like a normal class. These methods may be concrete or abstract. An abstract method is defined with the abstract keyword. It doesn't have a method body and must be overridden by its subclass. You'll find out more about how this works later. It is important to remember that if a class has at least one abstract method, it must be declared abstract. To demonstrate how this works, you can build on the abstract button class to include an abstract method called button press. This method is abstract. Its body doesn't contain any statements within curly braces. But what does the button press method do? This is where you add your concrete method, which defines the abstract method's purpose. Your app requires two concrete methods: setCaption and getCaption. When called, these methods set and retrieve a button caption. You're making good progress on your app. So far, you've created your abstract class, abstract method, and concrete method. Now you need to add a send button for your users to send messages. You can create a send button object using a subclass. However, it's important to remember that you can't declare an object of an abstract class. Java compiler immediately reports an error when you try to do so. As you hover the cursor on the error line, the following error message appears: abstract class is abstract, cannot be instantiated. So what's the solution? With Java, you can declare a class that extends the abstract class. In other words, you can create your required buttons as extended classes. A concrete method in the abstract class may or may not be overridden by the subclass. In Java, the is-a relationship type between classes implies inheritance. In your app, the send button inherits the abstract button class. This means the abstract button class becomes the superclass, and the send button class becomes its subclass. You also need to use the extends keyword to establish inheritance. When you declare any subclass that extends the above abstract class, Java warns you to declare it as an abstract or override the abstract methods. To ensure the send button class works as required, you need to establish the following instance variables. These are message, the message to be sent, and send to whom the message is to be sent. Now you need to provide a concrete definition of the abstract method button press. You can do this using override. Override is one of the predefined annotation types defined in the java.lang package. It informs the compiler that the method overrides an element declared in a superclass. You can override the concrete method from the superclass if you choose to. Otherwise, the base class method will be used. Finally, you need to design your like and forward buttons. You can do this by designing like button class and forward button class subclasses. These provide concrete implementations of the abstract methods in the abstract button class. Great work! You've learned about abstraction, how abstract classes work, and how they use concrete and abstract methods. And, in doing so, you've helped to put together the foundations of a great social media messaging application. As a developer, you will often have to design multiple types of the same object, like buttons. With abstract methods, you can define a common interface that can be shared across all objects of the same type, like set characteristics for buttons. In this video, you'll learn how to build these common interfaces by exploring the advantages of abstract methods in Java. So, let's begin by asking what an abstract method is. An abstract method is a prototype declaration of the method without the body part. For example, you could use an abstract method that combines two numbers to find their total. Another example is the abstract draw method in a shape class. Subclasses like rectangle, circle, and others must implement this method, each providing its own way of drawing the shape. Similarly, the abstract compute_task method in a person class could be implemented by subclasses such as teacher, doctor, and so on, each calculating taxes according to their specific rules. Neither the abstract class nor the interface can be instantiated, but their subclass can be. A subclass that extends the abstract class or implements the interface must override it to provide a concrete definition of the method. So, why declare the method abstract if it must eventually be overridden? Why not declare it as a normal method in the base class? What is the advantage of using abstract methods? Let's try to understand with a few examples. When designing a hierarchy of related classes, you must start with a top-level view and consider the common minimum features. Take an animal hierarchy as an example. Every animal eats to survive, moves from one place to another, and makes a sound. All of these characteristics change between each type. Some animals eat meat. Others eat plants. Some walk, run, or crawl. And some animals bark, purr, or roar. So the abstract level functionality of the animal class includes three abstract methods: eat, sound, and move. Each animal is also identified by its subclass. For example, tigers, fish, and dogs are all types of animals. But in Java, you can't just state that X is an animal, as the concept of animal is abstract. Each individual example of an animal, like a tiger, must be defined as a subclass to distinguish it from all other examples in the animal class. This means that the animal subclass extends the animal class by giving a concrete description of the abstract methods: eat, sound, and move. This helps to distinguish each individual example. Any other animal subclass must override these abstract methods. Their implementation may differ. For example, in a fish class, the move method prints the message "a fish swims." Or in a horse class, the move method prints the message "a horse gallops." As you discovered earlier, an interactive button is an example of abstraction. In its most general form, a button is an abstract class with abstract methods that describe its purpose. For example, does it create text or an icon? These methods include examples such as setText, setIcon, or onClick. You first determine the common functionality of a button. Then you can declare a subclass as having its own implementation of the abstract methods. For example, you can create a simple button class as an extension of the button superclass. When clicked, the simple button prints the statement, "Hello World." Likewise, you can design a radio button or a toggle button class to perform a specific action that overrides the abstract methods from the button superclass. For example, you could include code that changes the state of the toggle button when clicked. In this video, you learned that the principle of abstraction is important when designing a hierarchy of classes with related functionality, like buttons for an application. Abstract methods help you to define a common interface. Even though each one may have a different implementation in different subclasses, as the animal and button examples emphasize. This knowledge is a great start to your career as a Java developer. Abstract methods allow you to save time coding by using inheritance to build variations of objects. When designing a car, a manufacturer begins by crafting a blueprint explaining how the different parts relate. Likewise, when designing a software application, you must start by designing a class hierarchy, identifying the classes, and determining how they relate. Over the next few minutes, you explore the basics of class hierarchy in Java by learning to identify concrete and abstract classes and the relationships you can establish between them. You'll be able to use these skills to create hierarchies for any kind of project. Mega Games, a leading video game company, needs your help to create a new racing game in which players race against one another in vehicles like cars, trucks, and motorcycles. You can help Mega Games design these vehicles using class hierarchies, identifying the concrete and abstract classes, and establishing the correct types of relationships between the classes. Let's begin by determining the relationships you can establish between the vehicles. The game lets players race cars, trucks, and motorcycles. These vehicles have common characteristics like wheels and engines, but also many differences. Some have larger wheels, and others have more powerful engines. Defining vehicle as a concept or an abstract class makes sense in this context. It represents the broader concept and defines the core functionalities that all vehicles share. However, since it's abstract, you can't directly create objects. Instead, you can create individual vehicle objects like cars, trucks, and motorcycles as concrete classes. Each of these classes can inherit attributes from the abstract vehicle class. However, they can also have unique attributes. For example, you can create a car class with a powerful engine and a truck class with large wheels. Now that you've identified your hierarchy's abstract and concrete classes, you must determine their relationships. Are they an is-are relationship or a has-are relationship? In reality, a complex collection of classes involves both types of relationships. Let's identify instances of these relationships in your hierarchy, beginning with defining the relationship between the vehicle parent class and its child classes. As established earlier, a car is a vehicle, a truck is a vehicle, and a motorcycle is a vehicle. So, an is-a relationship exists between the abstract parent vehicle class and the different vehicles or concrete classes that inherit its properties. Now that we've established the is-a relationship, let's identify the has-a relationship. Each vehicle you design has parts like an engine or wheels. And each part can be created as separate class with attributes and methods. So, you can say that this is an example of a has-a relationship. In other words, each car has a part like an engine. In Java, a has-a type of relationship is called composition. A class is composed of something. In this case, the engine class is part of the composition of the car class. As you discovered, Mega Games wants different types of vehicles in its game. They want players to race everything from sedans to SUVs, pickup trucks, quads, and dirt bikes. In Java, the keyword extends establishes inheritance between a child and parent classes. You can use the extends keyword to extend the class hierarchy and add these different types of vehicles as subclasses through a combination of is-a and has-a relationships. This amounts to a hierarchy of classes or multi-level inheritance. In this instance, an SUV is a subclass of car, which is a subclass of vehicle. An SUV is not a truck. Now that we've designed a hierarchy by establishing its classes and relationships, let's code it. Start by declaring the abstract vehicle class with two instance variables. registration number, and the engine object, which in turn is an object of the engine class. The engine object is characterized by its attributes. The first of these is its type, which could be a V6 or V8. The second is its capacity, which might be a 2.0 or a 1.5. Or it could even be a vast 5.6 liter. Next, you must further extend the abstract vehicle class by creating the car and truck classes. Begin with the car class. The car class inherits attributes from the vehicle class, but it also has additional attributes like make, model, color, and year of manufacture. Although car is still an abstract class, it has not implemented the start engine method. You can repeat this process to establish abstract classes for vehicles like trucks and motorcycles. Next, you need to create individual vehicles or car objects. One of the big selling points of this game is that it lets players race sedans. So let's build one. The sedan class is a concrete class that extends the car class. It has additional instance variables like doors. This class must implement the start engine method. Here, it prints a message that the sedan with its details has started. Again, you can repeat this process to continue building different types of vehicles. Great work! You've designed a functioning class hierarchy for mega games, identifying the concrete and abstract classes alongside the is-a and has-a relationships. You can also use these concepts to design class hierarchies for an endless variety of other projects. A family is one unit, but different relationships exist between each member. For example, a son is viewed as a child in his relationship with his father, who is viewed as the parent. Likewise, in Java, different relationships exist between elements of a class hierarchy. Although each element is related, some are parent classes, while others are child classes descended from these parent elements. In this video, you'll learn how to design a simple class hierarchy by exploring how to identify elements and implement relationships between them. You've just been hired as a Java developer by a university to develop an application that provides details of teachers and students. You can use a Java class hierarchy to create the framework or blueprint for this application. You'll first need to identify different objects in the hierarchy and determine their relationships. Since students and teachers are both persons, you can begin by defining an abstract person class at the top of the hierarchy. All other classes like employee, student, and teacher are descended from this person class. The person class also has an abstract getDetails method, which the subclasses must override. When the getDetails method is called, each subclass prints the details of its attributes. Next, you need to create the date class. Remember that there is a composition relationship between person and date. In this case, each person has a date of birth. So the relationship between person and date is a has-a or composition relationship. The date class requires 3 integer values: date, month, and year, returned using the getDate method. The getDetails method is abstract, meaning it is meant to be overridden by the child classes. Great! Up to this point, you've defined the abstract person class. Since a student is a person, the student class inherits the attributes from the person class, and it may have its own attributes. It also needs to implement the getDetails method in the person class. Similarly, there exists an is-a relationship in employee and person. Employee is a person. The employee class may also have additional attributes. Since it subclasses the abstract person class, it must implement the getDetails method. The next step is to create these classes and further define their attributes and methods. Start with the student class as an extension of the person class. Begin by adding the instance variables subject and teacher. Then, Provide a constructor for this class that returns the following information for each student: name, date of birth, teacher, and subject. Since it extends the abstract person class, it must override the getDetails method. The getDetails method in the student class prints the student information on the console window. You also need to define the getters and setters for the instance variables. Remember, there is a composition between student and teacher. The teacher class appears later. So you've successfully created the person and date classes and established a composition relationship between person and date. Next, let's create the employee class, where you will apply these relationships and add specific attributes and methods. This class is an abstract extension of the person class. However, different types of employees, such as teachers, clerks, and lab assistants, may exist. You will need to extend the hierarchy further to incorporate these different types. In addition to inherited members, you must add two variables: date of appointment for each employee's date of appointment as a date value, and salary as an integer value. You also need two abstract getter and setter methods for salary. Here, the setSalary and getSalary methods are abstract because the subclasses of the employee class will have different implementations. Now, you need to create the teacher class. The teacher class implements its ancestors' abstract methods, the employee and person classes. Note that the teacher class extends the abstract employee class, which in turn extends the person class, which is also abstract. Hence, the methods to be implemented by the teacher class also include the getDetails method from the person class. You also need to define a constructor for the teacher class that returns the following variables and related values: name, date of birth, date of appointment, subject, and qualification. Next, override the getDetails method in the teacher class to print out the values of the instance variables. The final task is to create the main class, a runnable class. Inside its main method, create three instances as follows: date 1 for date of birth, date 2 for date of birth of student, and date 3 for the date of appointment of the teacher. Then, declare a student and a teacher object. Call setSalary to assign a value to the salary variable. Call the getDetails method to retrieve the information for both the teacher and student classes. Now, it's time to test the code. Fantastic! You've defined the person, student, and teacher classes, set up their attributes, and implemented the necessary methods. Run your application to return information for Madhavan, the teacher, and Belinda, the student. Great! The code works, and you have the records you need. You've successfully built a class hierarchy for the university. They can now use this hierarchy to retrieve information about the students and teachers. With your new knowledge of how to design a class hierarchy, you can expand your class tree by adding additional classes to the person class to help store and retrieve information about other employees, like secretaries or administrators. In Java, interfaces offer a standard way to connect different pieces of code, ensuring compatibility and seamless interaction. In this video, you'll learn how interfaces can be used to solve the problem of multiple inheritance. Super Games is developing a new game called Frog Quest, in which players can explore a mysterious forest as a friendly frog character. The frog must be able to crawl, jump, and climb when on land, and swim when the player enters the water. The crawl, jump, and climb movement types are characteristic of a terrestrial animal, whereas the swimming movement characterizes an aquatic animal. So when Super Games develops a frog class, it must inherit these movements from both the aquatic as well as terrestrial classes. So, when Super Games programs the frog in Java, it must ensure it inherits from aquatic and terrestrial classes. However, this gives rise to the problem of multiple inheritance, which must be solved using interfaces. But what is an interface and how can it help to solve this issue? An interface is a useful feature in Java that defines a class's attributes and methods but doesn't provide an implementation. Instead, the interface is defined as a collection of abstract methods. Let's learn more about how interfaces can be used to solve multiple inheritance in Java. In object-oriented programming, the feature of multiple inheritance refers to a class subclassing more than one class. However, Java doesn't allow for multiple inheritance. But why is this? It's because it can cause a confusing situation called the diamond problem. Supergame's frog character is an excellent example of this issue. As you learned, the frog character requires the ability to move both as an aquatic and as a terrestrial animal. Supergames can create the frog class, which subclasses the animal class. This, in turn, overrides the abstract method called move. Next, the terrestrial animal class subclasses the animal class and implements the move method that tells the game when the frog must jump, crawl, or run. The aquatic animal class also subclasses the animal class and implements the move method. This tells the game that the frog needs to swim. But the Java compiler indicates an error if Supergames tries to build a frog class that inherits the aquatic animal and terrestrial animal classes. This error is revealed in the error message "class cannot extend multiple classes." This means the Java compiler can't resolve the conflict between move methods inherited from both classes. In other words, the compiler has encountered the diamond problem. Let's take a quick moment to find out more about this concept. The diamond problem is an ambiguity that arises when a single class inherits from two classes. In FrogQuest, the terrestrial animal and aquatic animal classes inherit from the abstract animal class, while the amphibian class, the frog, inherits from the terrestrial animal and aquatic animal classes. When mapped out in a diagram, these inheritances form a diamond shape. This gives rise to the diamond problem name. The terrestrial animal and aquatic animal classes may have different implementations of the abstract move method. This means that the compiler is now confused about which version of move should be copied to the amphibian class. The names of more than one class cannot appear in the extends clause. Any syntax attempting to extend classes B and C via class A is invalid in Java. So, how can Supergames solve this issue and create a frog that can move on land and in water? Java tackles the case of multiple inheritance with interfaces and a subclass that can implement the interfaces. Even though Java only allows a class to extend one superclass, it can implement multiple interfaces. An interface can be used to declare the abilities of a class. The interface, in turn, is defined as a collection of abstract methods. Supergames only needs to specify the method signatures, which include the method name, any arguments it needs, and the return type. Let's take a few moments to explore how Supergames can use this in FrogQuest. Java provides an interface keyword to define an interface. Remove the abstract move method from the animal class and include it in the movable interface. The implements keyword in a subclass's declaration indicates that it is responsible for providing a concrete definition of the abstract method in the interface. You can now declare a subclass that extends animal and implements movable. It needs to override the move method. When called, the move method displays a message that an amphibian animal jumps and swims. The subclass must extend its parent class and then implement an interface. A statement that doesn't do this raises the error expected at the extends keyword. It's also important that a subclass must implement all methods in a given interface. But what if a class only needs to use certain abstract methods in an interface? To learn more about how this works, let's develop an application for an educational institution that handles fees receivable from its students and salary payable to its employees, such as teachers and other staff. In this instance, the person class is the superclass for the student and employee classes. You must provide methods for computing grades and paying the school fee in a student class. There are also methods for calculating salary and tax in the employee class. But you can't place all 4 methods in a single interface. The student class only needs the first 2, while the employee class needs the other 2. To counter this situation, you can have 2 interfaces, a student interface and employee interface, one for each student and employee class. First, create the parent person class. Next, create the student interface. This has 2 abstract methods. Any class that implements this interface needs to provide concrete definitions. The compute grade method determines the grades. The pay fee method handles the fee payment process. The employee interface contains the other 2 abstract methods. The first is compute salary, which the employee class and any subclasses must implement. And there is also the compute tax method. A student is a subclass of person and implements a student interface. The student class defines a constructor for instantiating its object. It has also overridden the getDetails method to print the student details. Then you need to provide the implementations of the interface methods. Put appropriate programming instructions inside the compute grade method and define the pay fee method. In this instance, a simple print statement is used for the sake of demonstration. Similarly, the employee class extends the person class and implements the employee interface. The salary and tax computation procedure varies and can be a complex algorithm. However, the examples in this video are simplistic implementations for demonstration purposes. Next, consider Teaching Assistant as a subclass of the student class. This class already implements the compute grade and pay fee methods from the student interface. A teaching assistant also receives a salary in the form of a stipend. So, this class only needs to implement methods from the employee interface. A teaching assistant also receives a salary in the form of a stipend. So, this class only needs to implement methods from the employee interface. The teaching assistant is generally entitled to a fixed amount as a stipend and doesn't incur any tax. You should now understand how to use interfaces to solve multiple inheritance in Java. Great work! Keep learning about interfaces. You'll soon have seamless compatibility and interaction across your applications. After a tiring day, you relax at home, watching television. You pick up the remote and press a button to change the channel. You've just used the remote's interface to achieve the desired result. As a developer, the software applications you design will need to allow for many such practical interfaces. This video explores some examples of these and demonstrates how they are created in Java. The remote control you just used is an obvious example of an interface. Remote controls are common for devices such as televisions and sound systems. The remote control interface defines the essential buttons such as power, volume, and channel selection. This allows you to control different devices using a consistent interface. A smartphone is another type of interface. Regardless of the manufacturer, each one provides common features such as making a call, taking a picture, or sending a message. Do you use social media? If you do, when was the last time you tagged a friend? Once a post or message is created, buttons and icons allow users to tag friends or add images. Interfaces can be used to define the basic post-creation functionality, while each platform implements it with its own customization. If you've bought something online, then you've experienced another use of interfaces. E-commerce websites such as Amazon offer different payment gateways to customers to facilitate payment. A payment gateway is a platform, such as PayPal or Stripe, that acts as an intermediary in electronic financial transactions. Each gateway has its own processing logic but mainly involves two activities. First, authenticating and authorizing the customer, and then processing the payment. Java itself makes extensive use of interfaces in the standard library. The list, set, and map interfaces define common operations for working with collections of data. These are part of the collection framework, which you will learn about in the next course. Also, the comparable interface allows objects to be compared and sorted based on a preferred order. But for now, let's go back to those very useful remote controls. The buttons on your television remote control might change the channel or the volume. But consider the interface of apps such as a music player, a video player, or an image slideshow. What button functions do you think would be common for all of this? Typically, they would have a start or play button, a stop button, a pause or rewind button, and finally a way to move on to the next song, video, or image. You've recently started working with a social media company called ConnectSphere. You're part of a team developing the software for a new music player app. Your team leader has assigned you a specific task. You have been asked to write the interface code. The code that you build must provide the following three functions: play, pause, and stop. You decide that it should also include ways to control the volume or shuffle the track playing. Let's step through the code which will produce these elements in the correct order. The first step is to design an interface with abstract methods. Here, an interface called player contains three abstract methods: play, pause, and stop. Next, the player interface must be implemented. In this code, it will be implemented by a music player app. That app is represented in the code by the class called music player. Now you must provide concrete definitions of the three methods. This next piece of code focuses on play. In this code section, the overridden play method contains a string argument that prints out a message for the user. It shows that a track is being played and also lists the track's name. Okay, now the user will have a way to play the track. What's next? Well, the user will certainly need to be able to pause or stop the track. This code defines a pause, and then a stop method to provide exactly that functionality. Now, let's consider what else might be needed. Well, you had already decided that the user should be able to control the volume and also not have to play the same song all the time. This code will shuffle the playlist, and this will control the volume. Well done! The music player class now has three methods from the player interface: play, pause, and stop. In addition, two more methods are defined: the shuffle method, that shuffles the playlist, and the adjust volume method, which controls the sound level. Now, how you can declare an object of the music player class and call its different methods in the main executable class. First, declare the object. Call the play method by passing the title of the track to be played. Adjust the volume of the player to 50. Pause the player app. Finally, stop the app. When you run the code, you are told that the track playing is live might be a deep fake. The volume is set to 50 and the music is first paused and then stopped. Well done! You can now hand over code that provides all of the interface functionality requested by your team leader. And you've added extra functionality to show your initiative. Interfaces are encountered in all areas of daily life. This video has demonstrated some practical uses of interfaces in real-world applications and how they can be implemented in Java code. Abstraction can be achieved in Java using both abstract classes and interfaces. Since both seem to have a lot of similarities, you might wonder, when do I use abstract classes and when do I use interfaces? In this video, you'll examine the difference between abstract classes and interfaces, comparing their features so you know when and where to use each. The social media group Connectosphere is creating a new music streaming service for its users. Coding the service with Java is a complex process requiring interfaces and abstract classes. But when and where should Connectosphere use each tool? Let's quickly review the basics of each, then discover how Connectosphere uses them to build its streaming service. An abstract class is like any normal Java class, but you can't instantiate it. It must be subclassed to use any of the assets, attributes, and methods in an abstract class. So, what purpose does an abstract class serve? The abstract class essentially defines the common structure of a hierarchy of classes. Interfaces, on the other hand, specify the functionalities a class must have. But they don't provide the implementation details. Interfaces tell a class that it can perform actions in the way it sees fit. Unlike abstract classes, interfaces might be implemented by completely unrelated classes. To understand these differences better, let's find out how Connectosphere uses them. As you just learned, you can't instantiate an abstract class. Instead, it defines the common structure of a hierarchy of classes. Each subclass includes additional functionality over and above what the parent class has. Connectosphere wants colorful, floating shapes on screen while music plays. An abstract class is perfect for this. An abstract shape class can act as a parent class for specific shape classes like circles and rectangles. However, the subclass has one constraint. If abstract methods exist in the superclass, they must provide concrete functionality. The shape class doesn't refer to any specific shape. It defines the abstract method's perimeter and area. So, the quadrangle subclass must implement this. This class can be subclassed into rectangle and square classes. Connectosphere doesn't require any quadrangle object. This means it can make this class abstract. This class readily inherits the abstract methods from the shape class. So, any subclass of quadrangle must now override the perimeter and area methods. Connectosphere can follow the same process to build a square class. Connectosphere now has a hierarchy of classes starting with the shape class. The abstract class serves as a base class with shared properties and methods. It works best with a clear is-a relationship between classes. Since it may contain some abstract and concrete methods, enforcing a partial contract with its subclasses is best. Unlike abstract classes, interfaces might be implemented by completely unrelated classes. Connectosphere can use them to let users interact with the streaming platform. It can code a generic controller interface for its platform with start, pause, and stop methods. The Music Player app implements these methods as per its functionality. Users can call the start method to start their chosen track, call the pause method to pause the track, and call the stop method to close the app. You might already be familiar with the diamond problem. This is when Java doesn't permit you to build a class by extending more than one class, as the compiler suspects ambiguity. However, Java has no problem if a class implements multiple interfaces. This is because multiple inheritance in Java effectively means subclassing a single parent class and implementing one or more interfaces. In Connectosphere's platform, the buttons you just explored have two distinct categories of methods. One set controls the playback through play, pause, and stop. The other controls the volume level through increase and decrease options. Connectosphere can code a media controller interface using abstract play, pause, and stop methods. It can also create an audio player class that implements the media controller interface to implement those abstract methods as follows. The play method starts playing the audio. When pause is called, the player pauses. And users can call the stop method to stop playing the current audio. You can't specify more than one class in the extends keyword in the class declaration. But with Java, you can combine interfaces. This means that a declaration like interface A extends B is acceptable in Java. Interface A could be extended to multiple interfaces, like C. It becomes a collection of abstract methods from interfaces B and C. ConnectSphere can extend interfaces on its platform. It starts by declaring the volume controller interface to specify the volume controller functionality. Since an interface in Java can extend multiple interfaces, ConnectSphere can create the audio controller interface that extends the media controller and the volume controller interfaces. It can combine the media controller and volume controller interfaces in audio controller, which the audio player class implements. The audio player class can also implement the combined audio controller interface. Since it's already overridden the methods from media controller, it can provide the functionality for the increase and decrease methods. ConnectSphere has already created the play method that starts playing the audio, the pause method that pauses the player, and the stop method that stops the player. The increase method increments the volume level by a value given as an argument. Similarly, when called, the decrease method decreases the volume by the specified value. All versions of Java from 8 onwards permit interfaces with concrete methods. This means methods with functionality. The interface can have a static method with a method body defined. The implementing class cannot override such a method. One problem with interfaces before Java version 8 is that adding a new method to the interface means providing its implementation code in the same class. As a result, any interface changes resulting from adding a method also change the implementation class. The Java 8 version overcomes this limitation. You can now declare a concrete method with a default keyword. The implementing class does not need to override it, but may do so if needed. ConnectSphere's streaming service interface can use both abstract and default methods. ConnectSphere can add video playback through an interface implemented by the video player class. ConnectSphere service must implement the abstract methods, but it can use the default methods as inherited. This class can be used in the application to let users play, pause, fast-forward, and rewind videos. ConnectSphere has now built the basics of a great app using interfaces and abstract classes. You should now understand the differences between both and know when and where to use each. Great work! Well done on completing the first module in this course. You've hit the ground running and there are many more exciting discoveries to come. This video will cover the key concepts covered in each lesson. You'll be able to review and appreciate all the knowledge you've gained. Let's jump straight in. Your learning journey began with some basic building blocks of object-oriented programming in Java. You learned about abstraction, how abstract classes work, and how they use concrete and abstract methods. And it wasn't just theory. There was a demonstration of how this knowledge could be used to begin creating a great social media messaging application. This demonstration introduced you to the importance of the user interface in an application. To build on this, you then explored implementing interfaces more deeply. Using the framework of the same messaging application, you learned what interfaces are. You also learned how to create the abstract class. You discovered how to create an interface to send, react to, and forward a message. Finally, you learned how to implement the interface that had been created. Then, you put all of this new knowledge to work. You created code for an application that would allow users to draw shapes. Another key concept was how abstraction can remove complexities from the end-user experience. You discovered the signature of abstract methods and how they are used in a class hierarchy. Equipped with this foundation knowledge, you moved on to more complex concepts. You explored how to design flexible and reusable code, a skill that you can use in any project. First up was an in-depth exploration of the basics of class hierarchy. You learned to identify concrete and abstract classes and the relationships you can establish between them. You were shown an example of how to design a simple hierarchy and establish relationships. Then, you wrote your own code to create a similar Java hierarchy. This provided a framework for an application that could be used in a real-life situation. Another topic explored was the importance of class design and design best practices. The first of these was choosing a class name that reflects the class's purpose. Another tip is to use smaller classes with just one responsibility and follow the standard of encapsulation. Use the abstraction principle wisely in class design and only expose the user to what is relevant to them. You should also try to reflect the natural relationships between all classes. Classic design pitfalls were also discussed, and you found out more about what you should watch out for. The first was multiple inheritance issues. As you discovered, Java does not support multiple inheritance, which could cause the issue known as the diamond problem. You now know that you can create an interface containing abstract methods that the concrete class can implement. You also know that you can declare multiple interfaces if the implementing class doesn't need to override all the abstract methods in a single interface. Another theme presented was the real use cases of interfaces in software applications. Practical examples of using interfaces in real-world applications provided context. A practical demonstration followed. You were taken through the steps to create code that adds functionality to buttons. This specific example was for buttons to control a music player, but it probably sparked all sorts of ideas. No doubt, you were able to think of other situations where you could use this approach and create functionality for other devices. With this knowledge as a backdrop and foundation, you moved on to exploring more complex interface implementations. You learned about including interfaces in class hierarchy design. Then you had the opportunity to put all that you had learned into practice by writing code in a virtual environment. You began by refactoring the existing code to implement interfaces. You also created a working class hierarchy. This brought everything together. It incorporated many of the elements you had learned about, such as abstract classes, methods, interfaces, inheritance, and polymorphism. As you reach the end of this module, you have learned about advanced concepts of object-oriented programming in Java. This will become a key part of your software developer toolkit. You had an opportunity to create the type of code that you will be building in the future. You've shown your skill, and you're firmly on the path to becoming a creative programmer in Java. You wake up and check the time. To your horror, you realize that you slept through the alarm and you're now late. Perhaps you skip breakfast and rush to get ready and dressed. As you leave home to go to your course or work, you are fervently hoping that there will be no traffic jams or delayed trains. This is not only an incredibly stressful start to your morning, but it will possibly also affect your schedule for the whole day. Because sleeping through your alarm and then having to rush to get ready to leave doesn't happen every day, you could describe this kind of situation as exceptional. Exceptional events can happen during program execution as well. In this video, you will explore the concept of exceptional events in Java more deeply. As a developer, it is important to understand and recognize exceptional events. Knowing why they occur is central to being able to avoid them and prevent your program from crashing. So, what is an exceptional event in a program? It can be described as an unexpected behavior that occurs when your program runs or during program execution. The word unexpected means that it's not something that usually happens, but that it may have occurred for an underlying unknown reason. Just as unexpectedly waking up late could disrupt your entire schedule for the day, in programming, an exceptional event disrupts the normal flow of program execution. Before examining exceptional events, it is important to understand what the terms exception and error mean, both in general and in Java in particular. The term exception can be defined as leaving something out, not doing something on purpose, or not following a rule. An error, on the other hand, is a mistake or an incorrect action. In Java, errors and exceptions are related to some degree and are usually discussed together. However, it is important to be aware that there is a significant difference between them. You have already discovered that an exception in Java is an event or an abnormal condition that could occur during the execution of a program. It interrupts the normal flow of executing program instructions. Exceptions can happen during compile time and runtime. They can also occur in code written by developers. What is important to remember is that exceptions are conditions that can be recovered by using correct exception handling mechanisms. Errors, on the other hand, represent an abnormal condition that cannot be recovered. They usually indicate a serious problem that should never happen. Errors always occur at runtime and usually happen due to the lack of system resources such as memory. They are not meant to be handled in an application using exception handling mechanisms. It is crucial that developers are mindful of them while writing code. Another key concept to be aware of is that there are two classes that represent exceptions and errors. They are also named exception and error. Both error and exception are descendants of a class named throwable. This means that throwable is the superclass of all errors and exceptions, and it represents both. All three reside in a Java package named java.lang, which is the base package included by default in all Java source files. Depending on when an exception or an error occurs, they can be categorized as compile time or runtime. They are also known as checked and unchecked. Exceptions that occur during compile time are known as checked exceptions. This is because they are checked or known by the Java compiler. They may also be called non-runtime exceptions. Exceptions that occur during runtime are known as unchecked exceptions. Errors always occur at runtime, and because of that, they always fall under the category of unchecked. Just as exceptional events, such as sleeping through your alarm, happen in your daily life, exceptional events can also happen in a program while it is in execution. You now know some exceptional events in Java code are recoverable and some are not. Unexpected events will happen, but as you grow as a developer, you can sharpen your skills. With time and experience, you will learn to reduce errors, which are irrecoverable. And even though exceptions are recoverable, if correct exception handling mechanisms are used, you will also find, as your skills develop, that you are able to anticipate and avoid them. Everyone encounters unexpected events in day-to-day life. Some of these might have been avoided. For example, if you had checked the weather forecast before going on a walk, you might have remembered to bring an umbrella and wouldn't have gotten wet. On the other hand, some events can't be predicted. For example, a bus you hoped to take is cancelled by the bus company without any warning. If these types of events occur during the execution of a program, they are known as exceptions. When you are working as a developer, understanding this will help you to create more effective programs. This video provides you with more information on exception types and shows you how to differentiate between them. Have you ever been in an exam and wished that your teacher was sitting beside you to check your answers? With the teacher correcting things, there wouldn't be any mistakes in the answers you submit. As a developer, you are like the student and the compiler is like the teacher. It can check your code and indicate when something is not right. If the compiler is not checking the code written by you, then at runtime, the program can behave in an unexpected manner. In a previous video, you learned about how things can go wrong in a program and were introduced to the term throwable. As you discovered, a throwable represents any unexpected behavior or an exceptional event that occurs during program execution. A throwable can be an exception or an error. Errors and exceptions can fall under two major categories: checked and unchecked. In the case of exceptions, this categorization is based on whether it occurs during compile time or runtime. Exceptions that occur at compile time are known as checked exceptions. Exceptions that occur at runtime are known as unchecked exceptions. There's a specific reason for naming them in this way. In the case of checked exceptions, the compiler checks the code and signals that something is not right and that it needs to be handled. This means these types of exceptions are checked at compile time. In the case of unchecked exceptions, there is no checking by the compiler. So, if there is something that's not correct, it will pass on to the runtime. Then, at runtime, it explodes and everything comes to a standstill. These exceptions are usually caused by programming errors such as invalid calculations or accessing objects that do not exist. Let's explore how these two exception types might appear in your code. So, what would be an example of an unchecked exception? What if in your Java program you want to open a file on your computer and read it? To do this, you would need to tell the program the name of the file along with its file extension and where to find it in terms of the folder that it lives in. But what if the file has been moved to a different location or deleted from your computer? This is an exceptional situation. This code is designed to open a file in order to read its contents. You'll learn how to work with files in Java later, but for now, remember that using file input stream is the most common way of accessing a file. When you try to create a file input stream for the file that you want to read, the compiler complains that something isn't right. The compiler understands that there is a chance that the file may have been moved or deleted from your computer. So an error is indicated in line 9 of the code where you are trying to create the file input stream. If you hover the mouse pointer over the error, a message appears. The message says, unhandled exceptions, java.io file not found exception. The compiler means that the file you are trying to open may be missing or not found in the location you specified. This is a typical checked exception. The exception is indicated clearly as java.io file not found exception. It also says that it's unhandled. You must handle this in some way because if you don't, the compiler won't compile this code. You'll learn how to handle this kind of exception in a future video. Now, let's examine an unchecked exception. This code is trying to divide 10 by 0. It reads, int number equals 10 divided by 0, semicolon. Since the result of dividing an integer value by 0 is infinity, Java obviously doesn't support it. So, while the compiler isn't currently flagging any issue, it will cause a problem. When the program is run, Java runtime notifies that a division by 0 has been attempted, and it also clearly specifies the line number where it happens. Also, the exception is indicated as java.lang.arithmetic exception. Even though the compiler would not force you to handle this, it should definitely be avoided by using correct coding and testing. You now clearly understand the difference between a checked and an unchecked exception. As you can appreciate, they both need to be handled effectively to prevent issues arising during runtime and interrupting the normal flow of your program execution. Understanding this will help you to write code that runs smoothly and does not create issues later on. Last week, after a long search online, you finally found the perfect gift for someone who is having a significant birthday. Excited, you clicked to add it to your shopping cart, only for the app to tell you that you can't because the item is out of stock. Now you have to find a different present. What a disappointment! But imagine if the ordering system didn't check that the item was in stock and let you complete the order. It might have been some time before you discovered that your carefully chosen gift wasn't available. Perhaps you might not have discovered it until it was too late to order something else. So how does the program handle your request in this situation? When you try to order an item that doesn't exist, you are attempting to perform an invalid operation. Similar situations can occur in programming, and they could cause exceptional behavior. Let's examine some of them. Mistakes do happen while writing code. Just as you end up getting things wrong in your day-to-day work, when writing code, you might end up doing the same. Mistakes in code can lead to unchecked exceptions. So what exactly are unchecked exceptions? Imagine you are writing code that has to divide one value by another when the program is run. That seems simple enough, you think. But what if you haven't allowed for the fact that one of the values could potentially change to 0? Division by 0 results in infinity. Obviously, infinity isn't a thing that can be represented in Java. When you attempt to perform a division by 0 calculation in a program, the Java runtime complains that it is not a valid operation. Developers can unknowingly introduce this and other similar mistakes into their code. Even minor programming mistakes can bring an application to a standstill by causing exceptions. The exceptions caused by such programming mistakes are known as unchecked exceptions. This is because the Java compiler doesn't check your code for these types of mistakes. Instead, it relies on you, the developer, to not make errors in the code. However, the Java runtime detects them and raises exceptions when you run the program. This causes your program to crash or break. This is why these exceptions are also known as runtime exceptions. Checked exceptions can be caught, declared, or thrown from code using the throws keyword which you learned about in a previous reading. However, the throws keyword is not meant to be used for unchecked or runtime exceptions. These exceptions are ideally meant to be prevented by developers with mindful coding and thorough testing. In Java, runtime exceptions are grouped into a hierarchy of classes. The runtime exception class is a subclass of the java.lang.exception class. It includes all the possible exception types that can occur at runtime. This means it is the parent or the superclass of all the different subclass types of runtime exceptions. Subclass types that represent common mistakes in code are arithmetic exception, null pointer exception, and finally, array index out-of-bounds exception. Now let's explore how these particular types of unchecked exceptions could occur in your code. An arithmetic exception occurs when an arithmetic operation results in an exceptional situation. Remember that divide by 0 scenario discussed earlier. Let's observe how that would create an exceptional situation. Create a new Java class named uncheckedExceptions1. Add a main method. In the main method, add code to divide 100 by 0 as int number equals 100 divided by 0. Nothing seems to be wrong here. The compiler doesn't complain about anything. Now run it. An exception is displayed in the console, indicating that an arithmetic exception has occurred in the main method due to a division by 0. In that example, you might have thought that the exception was obvious. However, imagine working with a large program that has many lines of code with many methods. In that situation, it could be difficult to spot this type of calculation error. Another type of unchecked exception is the null pointer exception. In Java, there are two kinds of memory, the stack and the heap. All variables that you create in your Java program are stored in stack memory. The heap memory is a special area of memory that stores objects. Variables can have a data type that could be primitive or non-primitive, which is also known as reference. A variable that has a reference data type would have an object as its value. Put simply, this means that the variable is referring to or pointing to an object. But what if it is pointing to something that is empty? If you try to access an empty reference variable and perform some operation on it, the Java runtime complains with a null pointer exception. This is like the ordering system telling you that the gift you tried to add to the cart is not in stock. This is how it really happens in your code. Create a new class named uncheckedExceptions2. Add a main method to it. In it, create a string type variable called name. In Java, strings are treated as objects. So a string is essentially a reference data type. At runtime, the variable name is stored in stack memory. Assign a null value to it. This means that the variable name in stack memory is pointing to nothing in heap memory. In other words, it's empty. Now access the string and print its length by calling its length method. Run the code. Notice that there is a null pointer exception. This has happened because the string is null and doesn't point to anything. When coding with Java, it's important to remember that you simply cannot perform any operation on a string that's null. This video has explored and demonstrated the action of unchecked exceptions in your code. You now know that they exist to prevent unexpected behavior in your Java application due to programming errors or mistakes. This knowledge provides a strong foundation for how you will design your code. As you move on in your software developer career, you will gain experience and expertise in designing foolproof and effective code. Tony is planning to take another long trip across the United States. This time, he wants to travel in more luxury and is considering buying a new car. He asks his work colleague, a car enthusiast, for their recommendation. He hears about a particular make of car and its features, such as its engine capacity and how it performs with acceleration or braking power. In Java, an exception object also has characteristics and behavior. This information is extremely helpful when you are dealing with exceptions in your program. This video explains what an exception object is. It demonstrates how and when they are generated by Java. It also introduces you to significant and useful information that you can find contained within an exception object. The car recommended by Tony's colleague is an instance of the car class. Similarly, an exception object is an instance of an exception class. By now, you know exceptions in Java come in a hierarchy of classes. The throwable class is the base of the topmost level parent of all exception and error classes. Exception is a direct subclass of the throwable class. It contains all the different types of exception classes as its subclasses. Remember the previous example of your code trying to open a file that doesn't exist? When this exceptional event occurs, Java creates an object of the specific exception type and hands it over to the Java runtime system. That is what's known as the exception object. The type of an exception object is always the specific type of exception that occurs. You explored a couple of these: null pointer exception and arithmetic exception in a previous video. Another is the array index out of bounds exception. Tony's colleagues recommended a particular make of car, and all cars manufactured by that car brand would have similar features and capabilities. The topmost superclass of all of these exception object types is exception. As a result, all exception objects have a set of common characteristics, features, and behaviors. They give useful information about the exception, including its type, where it occurred, or the exact location in code, such as the method and the line number. You will find this information extremely helpful when you are debugging your program to locate and identify a problem. Let's examine the exception object using some code. This code defines an array of integers that contains 5 elements in it. Note that in line 7 you are trying to access the element at index 5. Run the program. This produces an array index out of bounds exception. This is because the array has 5 elements, which means the last index is 4. There is no 5th element, or index 5, in this array. Remember, computers start counting as 0, so the 5th element is actually position 4. Because what you are trying to do is incorrect, Java creates an exception object and hands it to the runtime system, which is what's printed in the console. The exception object itself contains a lot of helpful information. It shows what type of exception occurred and describes it. The exception object also shows the exact location in the code or the line number where it occurred. In this example, the type of exception is array index out of bounds exception. It also clearly mentions that the reason for the exception is the attempt to access a 5th element that is out of the boundary of an array whose length is 5. Then it gives the method in which the exception occurred, main method. It also displays the exact line number in the code, line number 7. Now, let's explore another example. This code declares a string variable named message. Remember, a string in Java is treated as a reference data type, so message is a reference variable that points to an object in the heap memory. However, in this case, message is assigned to null in line 5, which means it's pointing to nothing in the heap memory. Now run it. It produces a null pointer exception. This happened because you are trying to find out the size of the string by calling the length method, but the string isn't pointing to any value. The Java runtime flags the invalid action. Then it creates an exception object and hands it to the runtime system. The runtime system prints it out in the console. Notice that the exception again gives you important and useful information. It identifies the type of exception, null pointer exception. It shows that it happened because you tried to invoke the length method on a string object that's null. It also gives the location in which it occurred, the main method, line number 7. The information that these exception objects contain is extremely helpful when you are debugging your code to locate a problem. Understanding and utilizing exception objects is a fantastic tool in your programming skill set. When problems occur in a program, exception objects can save you valuable time in the debugging process and help you to fix issues quickly and efficiently. This video explained what an exception object is and demonstrated how it is created and used. It also explored how much information can be found within an exception object. You are now aware of how useful exception objects are. But how can you catch them in your code? Don't worry, you will learn how to do exactly that in the next lesson. You worked hard creating your first program, but when you ran it, it terminated with an error. A little disappointed, you sit back and wonder what the best way to handle this is. After a minute, the answer comes to you. Use a try-catch mechanism. You remember the example of a mountain climber using a rope and safety harness while they climb. You realize that you can use the try-catch mechanism as a similar safety device while you're sorting out the errors in the program. Over time, the code you create will be more creative and designed to carry out more complex and adventurous actions. Of course, the daring acts you perform in your code might cause some exceptions. You need to use some protective gear to keep your program safe and prevent it from crashing. This is precisely the role of the try-catch block. It is important to be clear on what each part of the try-catch block does. In your program, the try block should enclose the section of code that could cause an exception. The catch block should contain code that handles the exception. This is the code that needs to run if the exception occurs. As you know, exceptions can be checked or unchecked. Checked exceptions are flagged by the compiler. Unchecked exceptions, on the other hand, are only apparent at runtime. A key benefit of a try-catch block is that you can use it to handle both checked and unchecked exceptions. So, you are probably wondering, how exactly do I write this safety mechanism into my code? Here's your opportunity to observe how you create the try-catch block step by step. To begin with, this is how you can create a try-catch to handle a runtime exception which occurs during program execution. First, create a new class by right-clicking on package L2. Then select New and then Java class. Give the class name as try-catch-test. Press Enter to create the class. Next, type main to add a main method. Select the main method from the drop-down to create it. In this code, you will assume that you need to perform integer division in your program. To achieve this division, you will use the simple division operator /, which takes two integers as input and returns their quotient. You perform integer division in Java by using the division operator. To do this, first declare two integer variables. For example, type int a equals 10 and int b equals 0 on separate lines. Then, type int result equals a/b to perform the division. Obviously, it's important that you know if what you've done is correct. The IDE indicates that there is a problem by underlining the code in yellow. To find out more, hover your mouse over the B marked with yellow. The Java runtime notifies you that this operation may cause an exception if you try to divide by 0. This happens because the denominator b is 0. It indicates that this situation should be handled. So what is the next step? This is the point where you can place this statement within a try block. Type a try block to surround the code. Try block is like the safety harness used by a climber. The line of code within it is now protected by the try block. Next, you need to add a catch block that says what to do in this case. The catch block should be typed below the try block. It should have one parameter, which is the type of exception that it handles, in this case, the arithmetic exception. While you could set a catch block to handle the overall superclass type exception, it is best practice to handle the specific subtype of exception if you know it. Type arithmetic exception as the exception class type and E as the exception object as a parameter to the catch block. The catch block can contain any code, but here it will be set to produce a meaningful message. Type system.out.println, open parenthesis, double quote, division by 0 is not allowed, exclamation mark, double quote, close parenthesis. Run the code again. Notice that instead of generating an error, the try-catch mechanism displays your message. This would mean that the program would not be interrupted and crash. This video has taken you through the practical steps you take to add a try-catch block to your code. By familiarizing you with these steps, it has shown you how to handle exceptions whenever they occur. When your program unexpectedly terminated, you were a little disappointed. Now, you can return to it, knowing that your knowledge of try-catch gives you a way to resolve the situation gracefully. You're making great progress with building fantastic Java apps and handling errors to ensure they run smoothly. But what if a single piece of code in your app causes more than one exception? Is it possible to handle only one single exception at a time? Can a single try block handle multiple exceptions? In this video, you'll learn how to use multiple catch blocks to handle different types of exceptions and how these can be used to manage specific exceptions. You've just finished programming your latest Java application. You're now ready to check for errors and resolve any emerging exceptions. But despite your attention to detail and great programming skills, there is always a possibility that your code might be prone to more than one exception. For example, consider this code extract. The second line causes an array index out of bounds exception. This is because it attempts to access index 5 of an array with only 5 elements, starting at index 0 and ending at 4. It also causes an arithmetic exception because it tries to divide 10 by 0, resulting in infinity. But you don't need to worry about this. Java can handle more than one exception at a time, right? Unfortunately not. Only one exception occurs at a given time, and only one exception handler is invoked to handle it. Well, if that's the case, then why would we need multiple catch blocks or multiple exception handlers? Because the same piece of code could cause different exceptions at different times, depending on the data it works with, just like the one you've recently encountered. In this case, you can use a single try block with multiple catch blocks to handle all the suspected exceptions. Yes, you can write multiple catch blocks for a single try block. If an exception occurs, a catch block matching the respective exception is executed. So, how could you resolve the exceptions you encountered earlier? Let's begin by exploring an example of the syntax for a single try block with multiple catch blocks in Java. Start with the try block as usual and place a code that may cause an exception inside it. Then, include the catch blocks one after the other. Each catch block handles a specific type of exception indicated by its parameter. Here, each catch block should correspond to a different type of exception. Catch blocks should be ordered according to their specificity. A catch block for a more specific exception type should always be placed before the catch block for its generalized equivalent. For example, runtime exception is a generalized exception, and arithmetic exception is a specific type of runtime exception. So, if your code contains arithmetic exception along with other runtime exceptions which you may not be currently aware of, you can deploy multiple catch blocks to handle them. However, you must place the catch block that handles the arithmetic exception before the one that handles the general runtime exception. This is the correct way of handling multiple exceptions in Java. Let's surround the code with a try block. Then define two catch blocks, one to handle arithmetic exception and the other to handle runtime exception. Within the catch blocks, you can place the code to handle these exceptions. The exception object exception gives access to a method named getMessage. So, call the getMessage method on the exception object and print the message. This returns the message associated with the exception as a string. In your code, the arithmetic exception is thrown first with zero division because the assignment operator has right-to-left associativity in Java. This means that the expression is evaluated from right to left. Therefore, the output displays the message divide by 0. Let's try handling the general runtime exception before the specific arithmetic exception. Notice the error at line number 10. Let's find out the cause by hovering over it. It says the arithmetic exception has already been caught and suggests to delete this catch block. Why? Well, because runtime exception is the superclass of arithmetic exception, so we can handle the arithmetic exception also. This is why you must handle the specific exceptions before the general ones. However, if you are aware of all the exceptions that might occur in your code, you can avoid handling the generalized exceptions. For example, you could write a catch block to handle the array index out-of-bounds exception instead of the runtime exception in the previous code. Additionally, if you feel the need to have a catch block to handle general exceptions too, you can add one at the end, such as handling any runtime exception here. Great work! You've successfully handled multiple exceptions in the same code using multiple catch blocks. Your Java app should now run smoothly with no other issues. When working with multiple catch blocks, remember that each catch block can handle one specific exception type. And if more generic exceptions are required, order your catch blocks from most to least specific. Nobody likes to waste resources like electricity. Not only is it bad for the environment, but it costs money too. That's why you always switch off a light bulb or heater when you leave a room. You must also mindfully use resources like files or databases when programming. If your program heavily uses these resources, you must close them after your program is finished. With Java, you can use try with to close the resources automatically when finished. In this video, you'll learn to identify use cases for try with resources, learning how they are structured and used. By the end, you'll be able to manage your resources more efficiently. Imagine a large software company asked you to develop a new file reading application. You're progressing well and ready to test the application by reading a test file. You've already encountered the finally block, which can be used with the try block to place any resource cleaning up code. For example, if you open a file for reading, writing, or a database connection, you can close it when finished in the finally block you place below a try block. But this is a manual effort. You might forget to close the file, leave it open, and risk using resources needlessly. The try with resources syntax is an alternative to the traditional try-catch finally or try finally syntax. With try with resources, you are not burdened with manually closing the resources. It takes care of closing them once your code has finished using them. Any resources you declare within the try with resources block are automatically closed upon exiting it. So, it does the same job as the finally block in performing resource cleanup tasks, but more robustly. Let's take a moment to explore the process and syntax for creating a try with resource. First, create a try with resource class, adding a main method. Next, open the class using the try method. Then, declare a file input stream using the try method. The input stream must locate the required file by name within the directory. During this stage of the process, you might encounter exceptions or errors. For example, you might encounter a file not found exception or I/O exception. You'll need to resolve this using a catch block. Finally, add code to read the file's contents from the input stream. Once you've finished reading and closed the file, any resources you declared are automatically closed. This is a great high-level overview of the process. But what does it look like in action? Let's find out more by examining the syntax of a try with resource using a real-world example. The resource used in this example is a file from which the program reads data. A file input stream is used for this purpose. You will encounter file handling later on in this course. For now, you can simply focus on its usage with the try with resources. The first step is to create a new class named try with resources and add a main method. Make sure to add curly braces to your code. Now you need to open up the try with resources. Type try to configure the try method. Then open a pair of parentheses followed by a code block with open and close curly braces. Now you must declare the file input stream. You want to read the contents of a file named test.txt in the same directory. So, provide the file name and location to the file input stream. This opens up an input stream to the specified file. You can use the input stream to read the file's contents. It seems this has caused a file not found exception. This error indicates that the file you're trying to open may not exist in the given location. This common compile time or checked exception can occur when dealing with files. The compiler states that you must handle the exception before proceeding, so place a catch block below the try block. The catch block should handle the exception called file not found exception. So, place it in the catch parameter. The compiler suggests that you handle the more generic or top-level exception, the I/O exception. This is because the code you usually put within the body of the try block, which reads data using the file input stream, could also cause the more generic exception type, I/O exception. So, accept the suggestion and replace file not found exception with I/O exception. Add an exception handling code to the catch block and add code to print the exception message. You can then add the following code to read the file's contents from the file input stream a byte at a time until it reaches the end of the file, at which point the read method returns -1. The integer variable content holds 1 byte of data read at a time from the file input stream. The while loop loops through the file's contents until it reaches the end of the file. The file is read by calling the read method of the file input stream, represented by the FIS variable. Each round of while loop execution reads 1 data byte and stores it in the content variable. This continues until the end of the file is reached, which is when the read method returns -1. The value of the content variable is printed to the console. Before printing, the byte value is represented as a character. Great work! You can now read files without checking that you've closed your resources afterward. The Try with Resource block guarantees that the resources are automatically closed. Imagine you're visiting a pet store, admiring a tank full of colorful fish. A staff member is asked to catch a specific type of fish for you. They use a net, but without much care, they scoop other fish along with the one they intended to catch. The staff member chose the right tool, a net, but used it inefficiently. They must now spend extra time returning the fish they unintentionally caught to the tank and try again. In coding, catching exceptions is like using that net. When you write catch blocks, you are handling exceptions in your code. But if you're not careful, you might catch more than you intended. This brings us to the concept of catch-all exceptions. While the name might suggest that catching all exceptions is a good thing, it's actually something we want to avoid. Just like in the pet store, where you don't want to catch all the fish, in coding, you don't want to catch every possible exception indiscriminately. This video will help you understand what catch-all exceptions are and why it's important to avoid them. By the end of this video, you'll know how to write more efficient and clean code. Let's get started. You already know that Java's error and exception classes form a hierarchy. Here's a reminder of their hierarchy. The parent or superclass at the topmost level is throwable. Both error and exception are direct subclasses of throwable. The hierarchy is extensive, with many subclasses branching out from the main error and exception categories. For example, under error, you have specific errors like out-of-memory error and stack overflow error, which signal serious issues within the Java virtual machine. On the other side, under exception, you find more granular subclasses like file not found exception under I/O exception or arithmetic exception under runtime exception, which are more common in day-to-day coding. You can also download this diagram from the video resources if you wish to examine it more closely. When you are coding, your instinct may be to include a type high up in the diagram to catch everything that might come up in your net. If you catch generic types such as throwable and exception, you'll be catching all their subtypes of exceptions in a single catch block. It's like catching every type of fish in the net when you only want one specific type. Let's explore some examples. According to Java's exception hierarchy, throwable is the superclass of all exceptions and errors. Java allows you to use it in a catch block, but this is not recommended. Again, if you use a throwable in a catch block, there's a risk that your code will not only catch exceptions but also errors. You are not supposed to catch errors in your code. Errors are thrown by the Java virtual machine to indicate a serious problem exists, such as a stack overflow or an out-of-memory situation. Now, consider handling an arithmetic exception. If you specify the generic class exception in your catch block, you catch the arithmetic exception. But you also end up catching all other checked and unchecked exceptions. It's like catching every type of fish in the net when you only want to catch one goldfish. So how can you avoid these types of catch-all exceptions? What should you keep in mind? When creating exception handling code, avoid using throwable and exception as the exception class type in catch blocks. Instead, when handling unchecked exceptions, always try to find the class that best fits the exceptional event in your code. Finally, what should you do if you need to handle multiple exceptions in one try block? What would be the best practice? Place the catch block for the most specific exception in the try block first, followed by less specific ones. This helps ensure you only catch what you need to. In this video, you've explored what catch-all exceptions are, why they are a problem, and how to avoid them. Well done! As you continue developing code, remember to handle exceptions thoughtfully. Just like the staff member at the pet store who needed to focus on catching the right fish, you should aim to catch only the specific exceptions your code needs to handle. Doing so leads to smoother and more predictable outcomes. Imagine you're back in school and your teacher reviews your answers to tough questions. If there's a mistake, it's pointed out, and with some guidance, you fix it. Great! In programming, checked exceptions work similarly. They help you ensure your code is error-free by catching issues early on. In this video, you'll learn how to handle checked exceptions in Java, making your code more robust and reliable. Another way to think about exception handling is to think of it like a game of basketball. When a player catches the ball but can't shoot, they pass it to another player who's better positioned. Similarly, when an exception is caught in your code, it can be passed on to another method for handling. Just as the ball moves to the player most likely to score, exceptions move to where they can be best handled. Checked exceptions are a safety net that ensures your code can handle unforeseen issues, such as missing files or database connection errors. By now, you've encountered various exceptions in a variety of scenarios, like the I/O exception or the class not found exception. Let's dive into how to manage these exceptions using the try-catch mechanism to ensure your applications run smoothly. First, let's explore how to handle the class not found exception, which occurs when you try to load a class that isn't in the class path. Here, a red underline indicates where the exception occurs in the code. To handle it, surround the line of code in a try block as try followed by an open curly brace, the line of code, and then a closed curly brace. Next, you need to place a catch block below it with code to handle the exception. So, type catch, and then open a pair of parentheses to pass the parameter, and then open a pair of curly braces. You know by now that the catch block should define a parameter, which is the exception type it handles. In this case, it's a class not found exception. So, specify the exception class name within the parentheses and give the reference variable name, which in this case is E. The exception handling code should be placed in the catch block. Simply print out the exception message with a print line statement. Specify e.getMessage. Then run the code. It will print out a message from the catch block specifying the name of the class that was not found. This approach ensures your program handles the error gracefully without crashing. Sometimes, you might want to rethrow an exception to pass it up the call stack. Earlier, you learned the exceptions can propagate from a lower-level method to a higher-level one. For instance, if an exception occurs in method M1 and you don't handle it there, you can rethrow it to method M2, and so on, allowing the exception to be managed at a higher level. When an exception occurs, this call stack is searched for an exception handler, starting from the method where the exception occurred and proceeds through the call stack in the reverse order in which the methods were called. When a suitable handler is found, the exception object is passed to that handler or the catch block. Despite the usual behavior, if that catch block doesn't want to handle the exception, it can rethrow the exception using the throw keyword. Doing this propagates the exception to a higher level in the call stack. This technique is crucial when you need a more comprehensive approach to exception handling across multiple methods. Let's explore this with a code example. In this code, method 1 is where the class not found exception occurs. It's called within method 1, while method 2 is called within the main method. So the main method lies at a higher level of the call stack. Let's place a try-catch block surrounding the code that causes the exception in method 1. Now, without handling the exception in this catch block, you can rethrow it using the throw keyword. So, type throw and then the exception object E. You also need to declare that method 1 is throwing an unhandled class not found exception using the throws keyword. So, in the method signature, add throws class not found exception. There's a red underline in method 2, when method 1 is called. This is because the exception has been propagated to the next higher level of the call stack, which is method 2. Wrapping exceptions in custom exceptions allows you to provide additional context. For example, if you're handling a class not found exception, you can wrap it in a my custom exception to include more details, like the specific class path or configuration that caused the issue. This technique not only makes debugging easier, but also enhances the clarity of error messages. Let's explore how this works. Create a new class named myCustomException. It should be a subclass of the exception class. So type in extends exception. Define a private string field named additional info. Add a getter method for it. Create a constructor that initializes the field additional info. The constructor should also accept a throwable, which is the original exception object. Invoke the superclass constructor within the constructor by typing in superThrowable. That's it! You got it! That's all it takes to implement your own custom exception class. Now, back to the code that causes a class not found exception. In the catch block, you can type throw my new custom exception. You can pass the exception object E and some additional info into it. Assume you have a connection URL. For example, if you have a database connection link like this, you can pass both the error message and the connection link to your custom error handler, which will call myCustomException. Finally, make sure to indicate that method 1 can trigger this custom error by adding throws myCustomException to the method declaration. By mastering checked exceptions, you are enhancing your code's reliability and making it more resilient to unexpected issues. Rethrowing exceptions helps you manage errors at the right level in your application, while wrapping them in custom exceptions provides richer, more informative error messages. Just like the basketball player passing the ball to the best shooter, you're learning to pass exceptions to where they can be best handled. Use these techniques to build robust, professional-grade applications that stand up to real-world challenges. Imagine you're developing an inventory management application that helps employees track stock levels. Imagine further that a customer wants to purchase a product and checks the stock availability, but because of an unhandled error, the application crashes. These types of scenarios can disrupt the user experience and even impact business operations, such as causing order delays. Fortunately, by effectively managing unchecked exceptions in your code, you can ensure that your application remains reliable even in the face of unexpected errors. In Java, runtime exceptions are known as unchecked exceptions. The compiler does not catch them, so the software developer must handle them appropriately. In this video, you will explore strategies for avoiding common issues like null pointer exception and array index out of bounds exception, which are subclasses of the runtime exception class. Let's start with the null pointer exception. This is a common programming error that can occur whenever an object is declared but not initialized. This is an unchecked exception because the compiler doesn't explicitly force you to handle it. Create a class named item and add a string attribute called name to it. Inside the main method, create an object of the item class and add a print statement to display the item's name as output. Imagine retrieving an item's name in your inventory system, which hasn't been initialized yet. Let's run the code to observe what happens. Yes, the name of the item is null, because you didn't initialize it. Let's change the print statement to display the name of the item in uppercase as item.name.to uppercase parentheses. Remember, the item object's name was not initialized yet, so when you attempt to run this code, it returns the null pointer exception with this message. It means the program tried to call a method on a null object reference, indicating it hasn't been initialized. Let's continue by adding another attribute price to the item class and define the toString method that returns the name and price. Inside the main method, declare an item object, and inside a print statement, call the toString method on the item object to print the name and price. Note that the object is still not initialized. You've already understood that running this code will again give you the null pointer exception as output. So let's handle this exception as a precaution. Use the try-catch block and put the object creation and print statements inside the try block. Also use the catch block to handle the null pointer exception. Type a print statement that says error : attempted to fetch a null item reference. Now, observe when the code is run that the code prints the message as per your instruction on the occurrence of the exception. Another common unchecked exception in Java is array index out of bounds exception. This occurs when you try to access an array element using an index that's out of the array's bounds. For example, if you have an array with 3 elements, accessing the 4th element will trigger this exception. In the context of the inventory management application, you might have an array storing item details. If you have an array with 3 elements, its lower bound is 0 and upper bound is 2. Trying to give the index beyond these 2 bounds results in array index out of bounds exception. Let's explore this in Java, and let's say our inventory management system is for books. In the item class used in the previous example, let's add a constructor to initialize the object's name and price attributes. Now, in the main method, declare an array of item class with a size of 2. Initialize the 2 elements in the array with 2 products, pen and book, with 10 and 100 as price respectively. Define an integer variable named index to store the array index you want to access, such as 1, and add a print statement to display the item details at this index using the toString method. Run the code and you should get the name and the price of the book as output. Now change the value of the index variable to 3 and run again. Since this index is out of bounds, you should get array out of bounds exception being thrown by Java. To catch this exception, surround the variable definition and print statements with the try block and use the catch block to handle the array index out of bounds exception. Type a print line that says error : the given index is out of bounds. Run the code and you should get the message as output. In real-world applications, effectively managing these exceptions can significantly enhance the user experience. For instance, it's crucial to ensure users don't encounter crashes when searching for products or adding items to their cart. Great job! You've taken important steps to make your code more resilient by learning how to handle unchecked exceptions. In this video, you've learned the importance of handling unchecked exceptions in Java. You've also learned that all the unchecked exceptions are runtime exceptions. That's because they don't violate any Java-specific syntax rules. Addressing the null pointer exception and array out-of-bounds exception ensures your application remains robust and user-friendly. Remember, unchecked exceptions can be managed effectively with try-catch blocks and by providing proper conditional statements. Congratulations on completing Defensive Programming Error Handling. It focused on the typical errors and exceptions that can occur daily in Java. But great news! What you've learned in this module will have equipped you to recognize them and to deal with them. Just like the climber mentioned in an earlier video, you have successfully worked your way to the summit. Let's review the route you've taken and recap the concepts and techniques you've learned along the way. At Base Camp in Lesson 1, you were introduced to the concept of exceptional events that can happen in program execution. These are the unexpected behaviors that can occur when a program runs. As a developer, it is important to understand and recognize exceptional events. Knowing why they occur is central to being able to avoid them and prevent your program from crashing. You learned that these exceptional events can be defined as exceptions or errors. They are both subclasses of the throwable class. Exceptions, also known as checked exceptions, can be caught by the compiler and recovered by using correct exception handling mechanisms. Errors, on the other hand, are not caught by the compiler and always occur at runtime. They are not recoverable and are also known as unchecked exceptions. You started to climb a bit higher now. You learned that checked exceptions can be caught, declared, or thrown from code using the throws keyword. Exceptions can also be unchecked, which means that they are not caught by the compiler but appear at runtime. You observed a practical example of a divide by zero error scenario, generating a Java-lang arithmetic exception at runtime. These types of unchecked exceptions do not need to be caught or declared. The compiler doesn't force you to catch them, but their occurrence causes abnormal termination, which could be damaging. Hence, they need to be handled with efficient coding. A lookup sheet for exception types will be a useful resource in the future. It will allow you to check exception names and confirm whether they are checked or unchecked. But you also discovered another useful resource. The information embedded in every exception object can help you debug your program. You were also introduced to the try-catch block, which you can use to gracefully catch and handle an exception and prevent program interruption or termination. The try block encloses the code that might cause an exception, and the catch block is what performs the actual exception handling. Lesson 2 emphasized the importance of catching specific exceptions to handle them appropriately. It focused on handling exceptions in more complex scenarios. It began by using multiple catch blocks to handle different types of exceptions. You are also given a step-by-step demonstration of the appropriate syntax for a single try block with multiple catch blocks. Next up, a new concept, the finally block. As you discovered, the major benefit of the finally block is that its code is always executed. A finally block will always be executed after a try block regardless of whether an exception was thrown or caught. You now know that finally blocks are ideal for cleaning up code that performs actions, such as closing open files or database connections. It could also contain important information, such as status messages. And there is no danger that the code will be bypassed. Next, you learned about the concept of try with resources. The try with resources syntax is an alternative to the traditional try-catch finally or try-finally syntax. As you know, the finally block can be used to close files and other resources. But any resources declared within the try with resources block are automatically closed upon exiting it. So it does the same job as the finally block in performing resource cleanup tasks, but more robustly. Then you had the exciting opportunity to put what you had learned about try-catch blocks into practice in your virtual lab environment. You were asked to make existing code error-free using try-catch blocks. Well done on successfully meeting that challenge. You were now 2/3 of the way up the mountain. Lesson 3 of this module focused on preventative measures and best practices. You already knew from Lesson 1 that error and exception are both subclasses of the throwable class. But now you were introduced to the larger hierarchy of subclasses that branch out from the exception and the error classes. If you catch generic types such as throwable and exception, you'll catch all their subtypes of exceptions in a single catch block. Also, if you use throwable in a catch block, there is a risk that your code will not only catch exceptions, but will also catch errors. And catching throwable doesn't give you the exact reason for the exception. This catch-all approach is not the best practice and is definitely not recommended. Another technique introduced was rethrowing. As you discovered, this is a useful approach when a method is not equipped to handle an exception. Using the throw keyword, propagates it up the call stack until it finds a suitable handler. This is a more comprehensive approach to exception handling across multiple methods. Wrapping exceptions in custom exceptions was also explored. Again, keep best practices in mind. Rethrowing exceptions helps you manage errors at the right level in your application, while wrapping them in custom exceptions provides richer, more informative error messages. Finally, you put everything together in a practical lab, where you were asked to program defensively to avoid or handle unchecked exceptions. You used try-catch, finally, throw, and throws, and all in pursuit of a good cup of coffee. So, having reached the summit, you can pause and consider all of the useful and practical information you have gained on the way. You have learned fundamental concepts and skills that will enable you to adopt efficient defense mechanisms against potential errors in a program. And you can be confident that they are in line with best practice. Good job! You're playing an exciting new video game, advancing through levels, and achieving a high score. In fact, you're enjoying it so much you've taken the time to create your own personalized character. Imagine how you would feel the next time you logged in if all that history and customization had disappeared. So what ensures that you can continue right where you left off? Files and file handling is the key to having the game save your scores, progress, and settings between sessions. You've already worked with files, so you know that a file is a container for storing data on a storage device such as a hard drive or flash drive. Files can contain many types of data such as text, images, videos, or programs. Your game would contain both program files and settings files. Files are organized in folders or directories to make data easy to find. Understanding files helps you to understand how data is stored and managed on your computer. For example, file names don't just help you identify the file you want to open. They also provide other key information because they consist of two parts: the name itself and a file extension such as .txt. This file extension shows what type of file it is and indicates which program should be used to open it. File names may contain upper and lowercase letters, but operating systems handle them in different ways. This can cause confusion if you're moving files between different systems. On Windows, file names are case insensitive. This means that despite the use of uppercase letters, these three file names, which have combinations of upper and lowercase letters, are all considered to be the same file. On Linux, file names are case sensitive, so these three file names, which have combinations of upper and lowercase letters, are considered three different files. On Mac OS, file names are case insensitive by default. However, Mac OS can be configured to use a case-sensitive file system, where the three file names would be considered different files. Files can be different in a more fundamental way. They can be text-based or binary-based. Text-based files store data in a format that can be read and understood by humans. The content of these files is stored in a plain text and can be opened and edited using a simple text editor or other text processing software. Binary-based files store data as a series of bytes. They hold content such as videos or executable programs and often require a specialized software to open and manipulate. So, what common types of text-based files are you likely to encounter or work with? Perhaps the most common is a text file, which is a simple unformatted file that stores plain text and has a .txt file extension. You will also work extensively with JSON files. These files store structured data using a specific format. They are commonly used for transmitting data in web applications. For example, a user.json file containing user details might be used as a resource in your application's login process. You will also frequently work with log files. They record events, processes, or messages generated by software, for example, to log access requests on a server. As a developer, you will use them to help you monitor performance or to debug your code. You want your game to remember that you reached level 42 in the last session, or a word processing application to remember what language you use. Settings and preferences are often stored in another text-based file type, XML files, which store structured data using custom tags. You run a .exe file to install your game. This is an example of a binary-based file. If you've ever had to store or transmit large numbers of data files, you might have created compressed files such as zip files to reduce their size. These are also binary-based. As a software developer, knowing if a file is text-based or binary-based helps you to decide how to handle it. What common types of file handling operations will you need to allow for? You will have to open or read a file to access its contents. You will also need to modify a file by saving or writing data to it. You also might need to add data to the end of an existing file without overwriting its contents by appending. You will also have to delete temporary files or old log files to free up space, or rename a file after processing to avoid overwriting it. Of course, you will also have to manage files and directories. You will need to create them, list their contents, and delete them when they are no longer needed. Understanding these types of tasks and file handling in general is a crucial part of programming as it influences several key functions. In many applications, data needs to stay available even after the program ends. For example, your game needs to save your character customization so you can use it again. And a word processing application saves content in a document so you can continue editing it later. Files are a common way to share data between different programs or systems. For example, a .txt file created in one application could be opened in another. Programs often rely on configuration files to determine settings. For example, a Java application might read database configurations like username and password from a configuration file. Programs often create log files to track errors or important events. You can analyze these logs to understand the program's behavior or to diagnose issues. This video has demonstrated that file handling is a vital aspect of programming. It enables the structured and efficient storage, retrieval, and manipulation of data. By understanding and effectively managing file types, you can create powerful programs to interact with the real world. So, as you settle down for another gaming session, you're not back at level 1 because the game developer understood the importance of file handling and storing data beyond a single session. At Super Games, you're part of the development team working on an update for the company's most popular game. The update will allow players to customize their game settings, including controls, graphics quality, and sound levels. The game must locate the correct settings file, regardless of the operating system or installation directory. After discussion, you decide to utilize Java's file class to achieve this, and the file path will be a key piece of information. So, what is a file path? A file path is a string that represents the location of a file or directory in the file system. In programming, file paths are critical for locating files on your computer's file system, whether you're reading, writing, or deleting them. File paths can be absolute or relative. An absolute path is like giving directions from a central point. It specifies the complete path to a file or directory, starting from the root of the file system. In a Unix-based system, the root directory would be the /. In Windows, the C:\/ drive letter is the root directory. A relative path, on the other hand, is like giving directions from your current location. It specifies the location of a file or directory relative to your program's current working directory. If documents is the current work directory and there is a file called test.txt within it, the path to the file would simply be test.txt on both Windows and Unix-like systems. However, if the file is in a subdirectory of the current working directory, then the relative file path is different. For example, the working directory is documents and the subdirectory is called your details. On Unix-like systems, the path would be documents/your details/test.txt. On Windows, the path would be documents/your details/test.txt. As you sit at your desk working on the code for this new update, you are very aware that you will have to handle file locations regardless of the platform. Luckily, you know that the file class in Java is a flexible way to work with file paths and files. It greatly simplifies file handling and manipulation. The file class in Java represents files and directories and provides methods for performing various operations on them. These operations could include creating, deleting, renaming, and checking properties such as whether a file exists, if it's a directory, and its size. The leader of the development team for the Game Update development team has assigned you your first task: create code to organize all the project's documentation. There are different types of files stored in two main folders. The Documents folder contains one subfolder called Images. It also holds a text file called notes.txt and a PDF file called project.docs.pdf, which contains formal documentation. The Image subfolder holds an image file called diagram.png, which will be used in this documentation. You need to create a file path example class, which will manage this project's documentation folder. Your first step is to import the file class from the java.io package. This class provides methods for working with files and directories. Next, define the file path example class, which contains methods to check file and directory paths. The main method serves as the entry point of the program. Now you need to define the file path for the two files contained in the Documents folder, notes.txt and project.docs.pdf. But remember that the Documents folder contains a subfolder called Images, which contains an image file that also needs to be accessed. Define the path to the directory and then to the diagram.png file saved in it. Next, you should check if each of these already exists. Print its absolute path and determine if it's a file or a directory. Create a method to check if a file or directory exists. It should also print the absolute path and verify if it's a file or directory. Next, create a file object representing the file or directory at the specified path. Now use if and exists to verify whether the file is present. If the file is found, print the absolute path. Next, you need to determine if the path points to either a directory or a file and print the appropriate path. If the path does not exist, then ask for a message to be printed confirming this. Finally, print a blank line for readability in the output. Well done! Your code is created and now it's time to test it. Great! All the paths point to the directories and files as you planned. In this video, you've learned how to use the file class in Java to manage files and directories. By checking if files exist, retrieving their absolute paths, and determining whether they are files or directories, you can ensure that your Java program interacts with the file system effectively. Now you can smile and tick off a task on your to-do list. The launch of this game update now seems just a little bit closer. ConnectSphere is developing a new social media app for players of its most popular game. The app will allow users to upload their own text files and images. Correct handling of these files will be central to the app's success when it is released. In Java, two critical tools for handling file input and output are byte and character streams. In this video, you'll explore the differences between these two types of streams and learn how to choose the right one for your task to ensure your applications run efficiently and effectively. First, what is a stream? In general, a stream is a path along which a certain resource flows. In a computer system, the data moves from one place to the other in the form of a stream. You can simply state that a stream is the flow bytes from one point to another. In Java, a standard input stream is where the data entered by the user through the keyboard flows into the system memory. In a Java program, this would be the data flowing into the program. The standard input stream is called system.in. It represents an object of the printStream class that's pre-configured to take input from the keyboard by default. The data moves from the computer's memory to the display monitor or printer through a standard output stream. System.out represents the standard output device, which is usually the console. It's a printStream object designed for displaying information on your monitor in a formatted way. System.err is also a printStream object. It is normally used to display error messages, making it easy to separate regular output from program problems. Data can also enter and exit memory through other streams, such as a disk file or a network socket. Here, you can observe how the same process of input and output streams can be applied to different types of sources and destinations. Input stream and output stream are abstract base classes that define the foundation for all byte streams in Java. Character streams are built upon the foundation provided by the reader and writer abstract base classes. Streams will handle the image and text files uploaded by players using ConnectSphere's new app. There are two primary types of streams: byte streams and character streams. Byte streams are used in Java to handle raw binary data. They read and write data one byte at a time. They're versatile as they can work with any data type regardless of its format. Byte streams are particularly useful for processing files containing binary data, such as the app user's image files, audio files, or other non-text content. Byte streams preserve the integrity of binary data and ensure that the data is transferred exactly as it is. Byte streams used for reading are called input streams, and for writing they are called output streams. In Java, they are represented by the abstract classes an input stream and output stream. There are many byte-based stream classes. Among these classes, most appropriate for file handling are file input stream and file output stream. In the code, the file input stream object, nameIn, is used to read from a stream of bytes from any binary file, whether it's an image, audio, video, or other binary data. And the file output stream object is used to write bytes to a disk file. If you're copying a file byte by byte, the read method of the file input stream class reads and returns the current byte available in the stream. The write method of the file output stream class writes a byte passed to the write method as a parameter to the given disk file. Here, they're used with a try with resources statement to ensure that the stream objects are closed properly so that even if an error occurs, it prevents resource leaks. Recall, a try with resources statement is designed to automatically close resources when the block finishes executing. Character streams are explicitly designed for handling text data in Java. Rather than working with individual bytes, character streams handle all types of characters, including Unicode, using the Unicode standard by default. Other encodings can also be used if needed. They manage the conversion between characters and their underlying byte representations, using the character encoding schemes such as UTF-8 or UTF-16. The app user would lose confidence in the app if their files and images did not upload correctly. Character streams process text data accurately, preserving its formatting and encoding. This prevents issues such as misinterpreted characters or corrupted text, which can occur if binary-oriented byte streams are used instead. Byte-based streams don't indicate character size, which can cause handling issues. Encoding isn't stored in the file, so ensure the same encoding is used for reading and writing with character-based streams. When using character-based stream classes, those classes which are used for reading are called reader classes, and for writing are called writer classes. There are many character-based classes. Among these character-based classes, two of the most appropriate for handling files are file reader and file writer. File reader reads characters from the source file, while file writer writes characters to the destination file. This ensures the content is transferred exactly as it is, preserving the integrity of the text. The file reader object reads a single Unicode character from a stream of characters in a text file. An object of the file writer class is used to write all types of characters, including Unicode characters, in a text file. The read method of the file reader class reads and returns the current character available in the stream. The write method of the file writer class writes a character to the given disk file. The developers at ConnectSphere must also take into consideration the performance implications of using these two streams. Byte streams process data in its raw form without the overhead of character encoding or decoding. This makes them faster and more memory efficient when dealing with large files or binary content. Character streams introduce an additional processing layer for character encoding and decoding, which makes them more suitable for text files. However, it can also lead to a slightly slower performance than byte streams, especially for large files. So if the choice of byte streams and character streams depends on the application's specific requirements, what would ConnectSphere choose? Byte streams are the correct choice for uploading binary image files. For text files, where encoding matters, character streams are the better option, despite the slight performance overhead. In this video, you've explored the critical differences between byte and character streams in Java, and how to apply them effectively. You can ensure that your applications handle file input and output efficiently, just like ConnectSphere does with its file upload features. You're part of a team working with health provider HealthWave Technologies to develop a new patient record system. Patient records will be shared across all their international healthcare facilities. If a patient record arrives with garbled text or information, it could lead to serious medical errors. Incorrect character encoding could cause just such a dangerous situation. Your role on the team is to ensure that special characters in patients' information are consistently represented. To achieve this, you must understand the concept of character coding and how to implement it correctly. First, let's find out more about character encoding. This is the mechanism that allows computers to store and transmit text by converting characters into a specific binary format. It ensures that data is accurately represented across different systems, which is crucial in global applications. There are several common character encodings, each suited for different purposes. It is important to be aware of the features of each one so that you can select the most appropriate type to use in your program. For example, UTF, Unicode Transformation Format, is a standard for representing characters, including letters, symbols, and emojis across different systems and languages. There are various UTF formats. The first is UTF-8. This versatile encoding represents each character in 1 to 4 bytes and is capable of encoding over 1 million valid Unicode code points. It's the most common encoding used on the web and is compatible with many languages, making it ideal for international systems. The 8 in UTF-8 indicates that this encoding uses 8-bit, 1 byte, blocks at the minimal unit for encoding characters. The next is UTF-16. This uses one or two 16-bit code units to represent characters, which can be more efficient for languages with large character sets. It's commonly used in environments that require non-Latin characters, which include all characters outside the Latin alphabet, A to Z. HealthWave Technologies is an international organization, so the patient records contain international characters. It is vital that these characters are encoded correctly to avoid any misinterpretation of patient information. Because of this, you decide that your program should use UTF-8 or UTF-16 encoding. You might also encounter another encoding standard called ASCII, the American Standard Code for Information Interchange. It uses 7-bit binary numbers to represent 128 characters, primarily from the English alphabet. It's efficient for simple text, but since it lacks the ability to handle characters outside the basic Latin set, it would not be appropriate for the international scenario in HealthWave Technologies. Finally, there is ISO 88591, where ISO represents the International Organization for Standardization. This is part of a series of ASCII-based standard character encodings that offer broader character support. It encodes 191 characters from the Latin script. It's used throughout the Americas, Western Europe, Oceania, and much of Africa, and is the basis for most popular 8-bit character sets and the first block of characters in Unicode. Now that you've determined which character encoding would be the most suitable for this system to share patient records, how do you implement it? In Java, you can specify the character encoding explicitly while declaring objects of InputStreamReader and OutputStreamWriter classes. Remember that the default encoding may vary by platform. Specifying the correct encoding can prevent issues such as garbled text or loss of special characters. If you don't specify the correct encoding, your Java application might misinterpret the text data, leading to errors when reading or writing files. HealthWave Technologies is asking for a meeting to discuss the project, and you need to present code that will demonstrate your approach to the issue of multiple language character sets. Let's step through creating this sample code. First, you use an output stream writer wrapped around a file output stream to write data to a file named patientrecords.txt. The static method writeUTF-8 declares an object of outputStreamWriter class to write data. The UTF-8 parameter ensures that the file is written using UTF-8 encoding, since that can handle international characters. The write method adds patient names, including those with special characters like José Álvarez, to the file. Each name is followed by a new line character, open parentheses, \n, close parentheses, to separate them. Note that the file operation is enclosed with a try-catch block. Call the writeUTF-8 method from inside the main method. This will create a patientrecords.txt file in the project folder. Check the contents by opening the file. To read back the file, define a static method readUTF-8. Open the patientrecords.txt file with InputStreamReader. The InputStreamReader, wrapped around a file input stream, is used to read the data from the same file. Again, the UTF-8 parameter ensures that the file is read using the same encoding, so the characters are interpreted correctly. The read method reads the file character by character and prints each one to the console. This loop continues until the end of the file is reached. Reads the file until its end with the help of a for loop. The names of patients will be displayed on the console. Well done! This sample code will demonstrate to HealthWave Technologies that the new system can handle information for international patients correctly. But of course, you have to anticipate that converting the text may not always progress as smoothly. What issues might arise? If the encoding used for writing and reading data is mismatched, special characters might be misinterpreted, leading to unreadable text. If ASCII is used to write data that contains non-ASCII characters, there might be loss of data as they are replaced with different characters, which might result in unreadable or incorrect text. When systems use different encoding standards, text data can be converted from one encoding to another. However, this process can be tricky, as data corruption can occur if it is not done correctly. You anticipate that the HealthWave representative will ask about this issue. You decide to prepare a sample piece of code that will demonstrate clearly the issue and the possible data corruption. The sample shows what will happen if a file is written with ISO 8859-1 encoding but written into a file with UTF-8 encoding. Define another static method in the main class named readISO. To read the file with ISO 88591, use it as a parameter to the input-stream-reader object. Declare a string builder object named content, and use the append method to add each character from the patient record file to it, accumulating the file's content in memory. Now write the file contents collected in the string builder object named content to another file, patient records UTF-8.txt. It now has the UTF-8 encoding. When opened, the contents will show some garbled text, as the encoding while reading, which was ISO 88591, and writing, which was UTF-8, didn't match. You are now confident that you've sufficiently prepared on the issue of character encoding for your meeting. You can assure them that particularly sensitive information like patient records will be accurately represented and preserved across diverse systems. This video has demonstrated that understanding and applying the correct encoding in your Java programs not only prevents data corruption, but also facilitates seamless international data exchange, which is crucial in today's globalized environment. The HealthWave team is developing an application to handle large amounts of sensor data from patient monitoring devices. HealthWave is a global company with a large number of international healthcare facilities. The application will handle thousands of sensor readings from different countries. Storing this data in plain text would be slow and take up too much space. However, reading and writing this data as binary reduces the file size and improves processing speed. This ensures that the system can handle real-time data streams without missing a bit. In this video, you will examine the concept of reading and writing binary files using byte streams, learn why they are used, and explore their advantages. Why is reading and writing in binary format more space efficient and faster to process? Text files store data as characters using the default encoding of the operating system or software being used, which takes up more space than binary bits. On the other hand, binary files store data in the exact format in which it is held in memory. Binary file operations ensure that the data is stored compactly and can be accessed quickly. This is essential for maintaining real-time data monitoring and analysis for HealthWave's patients. In Java, data output stream and data input stream classes are used to write and read primitive data types to and from a byte stream. These classes are included in the java.io package. To read data from a binary file, an object of file input stream referring to a binary file is used as a parameter for the constructor of data input stream class. The HealthWave team might use data input stream to read sensor data from a binary file using some key methods it provides. The readInt method reads 4 bytes from the input stream and interprets them as an int, a 32-bit signed integer. This could represent a unique identifier for a sensor. Before moving on, it's important to understand signed and unsigned data types. Signed types can hold both positive and negative values, while unsigned types hold only positive values. In Java, numeric data types are always signed. A 32-bit signed type uses 1 bit for the sign, 0 for positive, 1 for negative, leaving 31 bits for the value. The read-float method reads 4 points and converts them into a float, which is a single precision 32-bit IEEE 754 floating point. This standard uses 1 sign bit and 31 bits for the value and can represent decimal numbers. This could represent the actual measurement from the sensor, such as temperature or pressure. The read UTF method reads a string encoded in modified UTF-8 format from the input stream. Modified UTF-8 is a variation of standard UTF-8 designed for the Java virtual machine to handle strings during file manipulation and serialization. Serialization is a technique to save an object's state of values to a file and later recover it with the same state. For example, it can be used to record the time sensor data was captured. Similarly, to write data in a binary file, an object of file output stream, referring to a binary file, is used as a parameter for the constructor of data output stream class. The HealthWave team may use data output stream to write sensor data to a binary file. This ensures that the sensor data can be accurately and quickly retrieved when it is needed. They can take advantage of some key methods. The writeInt (int_v) method writes 4 bytes representing the specified integer value to the output stream. This could write the sensor ID as an integer to the binary file. The writeFloat (floatv) method writes 4 bytes representing the specified floating point value to the output stream. HealthWave could use this to write the sensor measurement, such as temperature or pressure, as a floating point number. Another method, writeUTF (string str), writes a string to the output stream using modified UTF-8 encoding. It writes the timestamp as a UTF-8 encoded string. This would enable HealthWave to store complex text data such as dates and times. After reading the necessary data, the program processes this information. This could involve storing the data in a database, performing calculations, or updating a user interface. As part of the HealthWave team developing this application, you will have to know how to write and read from a binary file in Java. Let's step through an example. To write a binary file, you need to declare an object of data output stream class and pass it to an object of file output stream that refers to a binary file to be written. The HealthWave application will store the variables sensor ID, sensor value, and a timestamp. Generate a random float value for the sensor value using the random class. Remember, we are generating random values to simulate test data. In real software, random values are typically used only if required by the software specifications. Assign an arbitrary timestamp to be saved. The methods writeInt, writeFloat, and writeUTF of data output stream class are called. The try with syntax is used here to ensure that the file is properly closed after the writing operation. All the activity is done inside the public static void binary write method. Call it from the main method and run the main class. The file sensordata.bin will be created in the project folder. Since it is a binary file, it will show garbled data if you open in a text editor. Next, what about reading a binary file? In a similar way, a public static void binary read method is defined to read back the data from a binary file. You need to use the data input stream class with an object of file input stream as a parameter to its constructor. Call the readInt, readFloat, and readUTF methods inside a loop till the end of the file is encountered. Finally, call the binary read method from main and run the application. The sensor data is now displayed on the console. HealthWave must safeguard its critical patient information and sensor data by following best practices and ensuring it is reliably stored and retrieved without errors. First, always ensure that streams are properly closed after operations to avoid resource leaks. You can use a try with statement to ensure the data input stream is automatically closed when the try block completes. Robust error handling is crucial when working with binary files. Common exceptions include I/O exception, which can occur due to issues like file not found or read-write errors. In this example, any I/O exception during the write process is caught and handled appropriately. This ensures that the application can log the error and take corrective action, such as retrying the operation or alerting the user. It's also essential to anticipate and handle data corruption scenarios, which can lead to partial reads or writes. You must ensure the system can recover gracefully. Checksums or validation processes during both read and write operations can help detect and correct errors, ensuring the data remains consistent and reliable. Before HealthWave writes the data, a checksum is calculated. A checksum is a value generated by custom logic that consistently produces the same result for a given input. Here, checksum is calculated on the sensor value and is stored with the sensor data. Later, during the read operation, this checksum can be recalculated and compared with the checksum value to ensure the sensor data has not been corrupted. You've explored the essential techniques for reading and writing binary files using byte streams in Java. You've learned to handle large data efficiently, ensuring performance and integrity. With this knowledge and keeping best practices in mind, you will become a key member of the team developing HealthWave's new application. Have you ever wondered how a file management system like Microsoft SharePoint works? With SharePoint, you can create, move, delete, and rename files while maintaining data integrity and performance. How does this relate to Java? Java handles file operations by using its file class or the more advanced Java NIO. Whether backing up critical documents or organizing large volumes of files, mastering and understanding these two options is essential for your system's reliability. In this video, you'll learn the essentials and compare Java's file class and the more advanced Java NIO, or New Input/Output. We have already explored the file class, which is a fundamental tool for managing files and directories, with straightforward methods for creating, deleting, renaming, and checking the existence of files. It is your go-to tool for basic operations, like allowing a user to manage their files. It abstracts file and directory handling, simplifying file operations and hiding technical details, and allows you to interact with the file system without knowing the specific details of how it operates underneath. As your application scales, the demand for more efficient file handling grows. That's where option 2, the Java NIO, comes in handy. The Java NIO provides more advanced file management features than the traditional file class, including non-blocking I/O, that is, I/O operations without waiting delays, and a wider range of file operation tools. Imagine you have to develop an application similar to SharePoint. The application needs to handle thousands of file operations concurrently, such as backing up user data or syncing files across different servers. Java NIO's Files class, combined with the Path interface, which we will see in further lessons, provides more efficient and flexible tools for managing files. Back to the development of your own file management system. With methods like files.copy and files.move, you can easily manage complex file operations, and NIO provides more detailed exceptions. It is thus easier to diagnose and handle errors during file operations. First, you must decide between using the file class or the NIO. To help you choose, keep the following in mind. First, for simpler, synchronous operations, like managing small-scale user file uploads, use the file class. Conversely, NIO's non-blocking nature is more suitable if you have large-scale operations, like server-side file processing. Second, if you need better performance in high concurrency environments, then NIO's non-blocking I/O and advanced features are the best choice. And lastly, the file class is easier to implement for basic operations, while the NIO offers more powerful methods that pay off in complex scenarios. Let's navigate to IntelliJ and compare the file class and the NIO library in terms of creating, deleting, and renaming a file by introducing 3 scenarios. First scenario: a user uploads a new document to your application, and you need to create a new file to store it using the file class. The method createFileForUpload creates a new file in a specified directory with a given file name. It checks if the file already exists and returns a message indicating whether the file was successfully created or if it already exists. Therefore, the expected output of the createFileForUpload method depends on the state of the file system at the time the method is called. The output will be one of 3 possibilities. 1. If the file with the specified file name does not already exist in the given directory, the method will create the file and return file created successfully, absolute path to the file. Second, if a file with the specified file name already exists in the given directory, the method will not create a new file and will return file already exists, absolute path to the file. And thirdly, if an error occurs during the creation process, it catches the exception and returns an error message. Second scenario: what if you have to delete temporary files that are no longer needed? The file class makes this a simple and straightforward way to manage the deletion of temporary files in a Java application. The deleteTempFile method checks if the specified file exists at the given path and attempts to delete it. If successful, it confirms the deletion with a message. If unsuccessful, it notifies that the deletion failed. Last scenario: what if a user decides to rename a document? The renameFile method is designed to rename a file by changing its name from an old one to a new one. The method checks if the renaming operation was successful and provides feedback by printing a message, confirming whether the operation was successful or not. So how do these 3 scenarios relate to the NIO library? Let's explore. First scenario: a user uploads a new document to your application and you need to create a new file to store it. You can create the path object with paths.get to get the relative path and indicate the file's location as user_documents/uploadedfile.txt. Then, the files.createFilePath method attempts to create the file at that location. Second scenario: deleting temporary files that are no longer needed. With NIO, the files.delete method is used to delete the file at the specified path. As with the file class, NIO checks if the specified file exists at the given path and attempts to delete it. A message will be displayed in the console indicating success or error. Last scenario: a user decides to rename a document. NIO will rename the file by moving it from the old path to a new path using files.move. A confirmation message will be displayed in the console. What if your application needs to create regular backups of user files? This can be done with Java NIO as well as file class. A file is copied from one location to another by creating path objects for the source and target. For example, user_documents/userfile.txt and backup/userfile_backup.txt. The files.copy method then copies the file. The standard copy option .replace_existing option ensures that if the target file already exists, it will be overwritten. Finally, a message is displayed in the console confirming the file copy operation. File operations can sometimes fail due to issues like file permissions, missing files, or other unforeseen errors. Handling these exceptions is crucial to ensure your application remains robust and reliable. Proper exception handling not only helps in diagnosing and addressing issues quickly, but also ensures that your application can continue to operate smoothly without unexpected crashes or data loss. By anticipating and managing potential errors, you can maintain the integrity and stability of your application, providing a better user experience. In this video, you learned that you can use two methods to create a file management system: the file class and Java NIO. While the file class is perfect for simple, straightforward tasks, your file management needs might evolve. The Java NIO offers the performance and flexibility necessary for more demanding environments. By understanding both approaches, you can design your application to efficiently manage files, ensuring reliability and performance across various use cases. Whether you're handling basic user uploads or complex file synchronization tasks, Java provides the tools to get the job done effectively. Do you have a journal where you capture your to-do list? Imagine that the entries from yesterday disappear while you write in the journal. That will be frustrating. In this video, you'll explore appending data to existing files with the File Writer class, which allows you to add new data while retaining existing data. Connectosphere, a communication and networking solutions company, wants to create a new feature that appends each new activity log to an existing log file. This ensures that every interaction is recorded without overwriting previous data, allowing a complete history of user activities. Let's explore how to implement this feature by using a method that appends data to the file efficiently and reliably. Appending data is when new information is added to the end of an existing file without deleting the existing content. This is commonly used when continuous data logging or updating is required, like maintaining logs, transaction histories, or adding records to a data file. With Connectosphere, appending data is crucial for user interaction. For example, logins and profile updates that is recorded in sequence without losing previous entries. Therefore, maintain a complete and accurate history of all user activities. The File Writer class in Java is fundamental in writing data to files. With the File Writer object, you can specify to append or overwrite an existing file. For example, you can set the append parameter within the File Writer constructor to true. New data will then be appended to the end of the file. How does this relate to Java and Connectosphere? Connectosphere needs to preserve user interaction history. For example, login or profile updates are added to the activity log file. Let's explore how to add a new log entry to an existing file. Import the File Writer and I/O exception classes from the java.io package. The Activity Logger class represents a simple Java program that appends a new log entry to an existing log file named user_activity.log. It generates a log message with the current timestamp. Thereafter, a File Writer class in append mode to write this log entry to the file without overwriting any existing content. If the file doesn't exist, it will be created. The class also handles potential I/O exception errors that might occur during the file writing process, ensuring that any issues are properly reported. When you run the activity logger file, the data in the user_activity.log file will be updated, returning the message log entry added. The buffered writer class enhances the efficiency of file writing operations by buffering the characters before writing them to the file. This reduces the number of disk accesses, which is particularly beneficial when dealing with large amounts of data or frequent write operations. For ConnectSphere, using a buffered writer with a file writer class can significantly improve performance, especially in environments where the system needs to remain responsive under heavy load. In this example, buffered writer wraps around the file writer class, buffering the data before it's written to the file. This reduces the number of write operations, making it more efficient, especially in high-volume logging scenarios like those in ConnectSphere, where user activities are logged frequently. When you run the efficient logger file, the data in the user_activity.log file will be updated, returning the message log entry added efficiently. When appending data to files in Java, challenges like concurrent access and data integrity can arise. If multiple processes write to the same file simultaneously, data corruption may occur. Implementing file locking mechanisms is essential to prevent this. File locking ensures that a process has exclusive access to a file, avoiding conflicts and maintaining data integrity. This is particularly important in environments with frequent concurrent access, as it prevents conflicts and ensures accurate data, especially in systems that depend on reliable logs for auditing or tracking. Let's explore how to perform file locking. The SafeLogger class is a Java program designed to safely append a new log entry to the user_activity.log file, ensuring that concurrent access to the file is managed correctly. The program generates a log entry with the current timestamp and then uses a file channel to open the file in append mode. Before writing to the file, it acquires a file lock using file lock to prevent other processes or threads from modifying the file simultaneously, ensuring safe concurrent access. The log entry is then written directly to the file using the file channel object in append mode. By using file channel in combination with file lock, we ensure that only one process can write to the file at a time, preventing data corruption and maintaining safe concurrent access. Throughout the file writing process, any potential I/O exception errors are caught and handled appropriately. This includes acquiring the file lock, writing the log entry, and releasing the lock in the finally block. In this example, file locking ensures that only one process can write to the file at a time. This approach is crucial in the ConnectSphere platform to prevent data corruption when multiple parts of the system attempt to log user activities simultaneously. When you run the SafeLogger program, the data in the user_activity.log file will be updated, and the message log entry added with safe concurrent access will be returned. When appending data to files, it's important to follow best practices to ensure the reliability and maintainability of your code. These include 1. Always close file streams. This prevents resource leaks that could cause performance issues or crashes. 2. Use try with resources. This Java feature automatically closes resources, making your code cleaner and less error-prone. And 3. Handle exceptions gracefully. Ensure your program can handle errors without crashing, providing a smooth user experience. By implementing these best practices, ConnectSphere maintains a robust and reliable logging system, ensuring that logs are consistently accurate and that resources are managed efficiently. In this video, you learned how to effectively append data to files using the file writer and buffered writer classes in Java. You explored common challenges like concurrent file access and best practices for ensuring data integrity and resource management. By applying these techniques, you can ensure that your applications, like ConnectSphere, maintain accurate and complete logs, even as new data is continuously added. Searching for a file or folder on your computer often becomes a frustrating experience, especially when you are unfamiliar with the file hierarchy. It feels like hunting for a needle in a haystack without knowing which haystack to check. You might struggle to remember where you saved or need to save a file, or accidentally bury it in an unexpected folder with an unclear name. Navigating through countless folders and subfolders quickly becomes overwhelming. Without a straightforward method, you can lose your way clicking through one folder after another, hoping to uncover the missing file. In this video, you'll learn Java file navigation with the file and files classes to traverse directories and list files. This will help you develop programs that effectively manage and organize large file systems. ConnectSphere, a communication and networking solutions company, must optimize server space by archiving old media files. The development team must create a Java program that navigates directories to locate and move outdated files to the archive folder. This process is crucial for maintaining efficient server resource usage and ensuring optimal system performance as user data grows. ConnectSphere organizes its files within a primary directory named user_data, which contains various files and subdirectories. Therefore, effective file navigation involves traversing directories and files within a file system with programming techniques. In Java, the file class provides methods that allow developers to navigate the file system, retrieve information about files and directories, and perform operations such as listing directory contents and checking file properties. Therefore, ConnectSphere needs efficient file navigation to identify and archive outdated media files. First, let's define directory traversal. In Java, directory traversal involves moving through the contents of a directory with files and subdirectories. This is important for programmatically managing file systems. The file.listFiles method allows for simple directory traversal, returning an array of file objects representing the files and directories within the specified directory. For more complex cases like traversing large directories or accessing nested subdirectories, the files.walk method is more powerful. It provides a stream of path objects that can iterate over directory contents, making it suitable for large directory structures. Let's navigate to IntelliJ and explore directory traversal. In this example, the file.listFiles method is used to retrieve an array of file objects representing all files and directories within the user_data directory. This code iterates through an array of file objects, checking whether each object is a file or a directory. Based on the file type, it then prints the name of each item. While this method provides a straightforward way to list the contents of a directory, it only displays the files and directories at the top level, as it doesn't recursively traverse the file system. Therefore, the output doesn't indicate the files within the subdirectories. Another option is recursive directory traversal. The files.walk method is used to generate a stream of path objects that represent all files and directories within the user_data directory, including all its subdirectories. The filter method is then applied to this stream to include only regular files, excluding directories. The forEach method prints out the full path of each file. The try with resources will ensure that the stream is properly closed, preventing potential memory leaks. Since the code filters out directories like photos and docs, only the regular files will be printed. The full path for each file, starting from the user_data directory, will be displayed in the output. The files.walk method is ideal for handling complex tasks. Why? Because it simplifies recursion to browse directories. Normally, you'd need to write your own code to navigate through directories. But files.walk does that for you, going through each folder and generating a stream of path objects, making your life much easier. Secondly, Files.walk is built to handle complex directory structures. Whether you're dealing with a deeply nested folder system or symbolic links, Files.walk is designed to handle the intricacies of real-world file systems. There are also best practices for filtering and managing files. For example, when listing files and directories, it's important to note that you can apply advanced filters to retrieve only specific types of files by specifying the extension. The files.newDirectoryStream method allows you to filter which files are included. Conversely, the files.walk file tree method offers a more complex and customizable approach for advanced directory traversal. It provides precise control by enabling custom actions at each step of the process through the File Visitor interface, ideal for tasks that require detailed handling, like error management, skipping certain files, or processing directories in a specific order. When applying filters and managing files, you can follow two best practices. 1. Filter files as early as possible to reduce the number of files for processing, especially with large directories. This approach helps avoid unnecessary processing that can degrade performance. And 2. Always ensure that streams are properly closed after use to prevent resource leaks. Using try with resources is a reliable way to handle this automatically. In the ConnectSphere scenario, these best practices enabled the program to focus on relevant media files, ensuring that only those meeting the criteria were moved to the archive, thus optimizing storage usage. In this video, you learned how to navigate directories in Java using methods like file.listFiles and files.walk, manage subdirectories recursively, and filter files effectively. These skills are essential for handling large and complex file systems, as demonstrated in the ConnectSphere scenario. By applying these techniques and best practices, you can ensure efficient and reliable file management in any Java application. Have you ever wondered how file management works on a computer or cloud storage platform? You can create, delete, and rename files and folders to keep an ordered hierarchical system. For the system to work, data cannot get lost or corrupted. In this video, you'll learn how to manage directories in Java, from creating and deleting directories to renaming and resolving conflicts, ensuring your file system stays organized and efficient. Let's revisit ConnectSphere, a communication and networking solutions company that wants to implement a new online platform for users to join and interact. Upon registration, this feature will automatically create a dedicated directory for each new user, where their profile information and uploaded content will be stored. Therefore, careful creation, renaming, and deletion of these directories are necessary to keep the system organized and to ensure that no data is lost or corrupted during these operations. In Java, these operations are primarily handled using the file class, which provides methods to manipulate directories, ensuring efficient organization and storage of files within a program. The file class provides a simple and straightforward API for basic file and directory operations, making it suitable for quick tasks and legacy code. However, it lacks flexibility and advanced features like robust error handling and support for modern file systems. Conversely, NIO, with its path and files classes, offers a more powerful and versatile framework. It supports more complex file operations, better performance, and improved error handling through exceptions. NIO is better suited for modern applications that require advanced file system manipulation, like handling large directories, symbolic links, and atomic operations. Let's return to ConnectSphere. As a programmer at ConnectSphere, you will need to use NIO in the development of directory management features. The advanced capabilities of NIO will allow you to efficiently handle user data, ensuring that directories are created, managed, and maintained in a way that supports the platform's scalability and reliability. While file is useful for basic tasks, NIO is preferred for robust and scalable file management in Java, particularly in a high-performance environment like ConnectSphere. So, if NIO is so powerful, why not always use it instead of the file class? Well, it depends on the task. The file class is simpler and works well for quick, lightweight operations, like basic file creation, renaming, or deletion. If you're working on smaller projects or legacy systems that don't need advanced features, the file class gets the job done with less overhead. Let's look at the ConnectSphere platform. A directory is created for each user upon registration, using the Create Directories method from the NIO Files class. Before creating the directory, the code checks if it already exists to prevent overwriting any existing data. This precaution is essential for maintaining data integrity on the ConnectSphere platform. The directory example NIO program attempts to create a directory structure at the specified path user_data/Joe_Gray using the NIO files.createDirectories method. This method tries to create the directory named Joe_Gray along with any necessary but non-existent parent directories. Under typical conditions, where the directory does not exist and permissions are sufficient, the most likely output when running this program for the first time is a message confirming the directory is created successfully. If the directory user_data/Joe_Gray already exists, the program will detect this and print a message confirming this. If the directory creation fails, for example, due to insufficient permissions or an invalid path, the program will print a notification that the directory could not be created. Renaming directories is necessary when data identifiers change, such as when a user changes their username. The associated directory must be renamed to reflect this change, ensuring consistency across the platform. In Java, while the file.renameTo method can be used to rename a directory, it has limitations, such as not supporting cross-file system renaming, like if the source and target locations are on different file systems, such as different partitions, drives, or networked file systems. Instead, NIO's file.move method provides a more robust solution that overcomes these limitations. The directory rename example NIO program attempts to rename a directory from user_data/John_Doe to user_data/John_Smith using the NIO files.move method. The output depends on several factors, such as whether the source directory exists and whether the name operation succeeds. If the directory user_data/John_Doe exists and there are no issues with permissions or other factors, the most likely output when running this program would be: if the directory user_data/John_Smith does not exist, the program will print a message confirming the directory is successfully renamed. If the rename operation fails, for example, due to insufficient permissions, the target directory already exists, or an invalid path, the program will catch the exception and print an error message. Additionally, it will print the stack trace of the exception to provide more details about the failure. Deleting directories is crucial for cleanup operations, such as when a user deletes their account on ConnectSphere. Proper deletion ensures that no residual data is left behind, maintaining the system's cleanliness and performance. The NIO files.delete method is useful for this purpose, but it's important to note that it only works for empty directories. If the directory is not empty, the method will throw an exception. This method provides detailed error handling, allowing you to catch and manage exceptions if the deletion fails due to non-empty directories, permission issues, or other factors. Let's explore the nio files.delete method. This directory deletion example program attempts to delete a directory at the specified path user_data/Joe_Gray using the files.delete method. If the directory is successfully deleted and the directory is empty, the program will print a message saying the directory has been successfully deleted. If the directory deletion fails, for example, the directory is not empty, the path is invalid, or there are insufficient permissions, the program will catch the I/O exception and print an error message. This example highlights the use of NIO for directory deletion, demonstrating its ability to provide detailed error handling. In ConnectSphere, robust error handling is essential to maintain the platform's reliability. For instance, when deleting a user's directory, the platform must ensure that all associated files are deleted first. If an error occurs, it should be handled gracefully to prevent data corruption or loss, which is critical for maintaining user trust. When performing directory operations, the code first checks if the source directory exists before attempting to rename or delete it. This avoids errors related to non-existent directories. The files.move method is used with the standard copy option .replace_existing option, ensuring that the operation can overwrite an existing directory if necessary. Exception handling with a try-catch block ensures that any issues during file operations, such as I/O exceptions, are caught and managed appropriately, preventing unexpected crashes and preserving data integrity. In this video, you learned how to manage directories in Java, from creating and deleting directories to renaming and resolving conflicts, ensuring your file system stays organized and efficient. Mastering directory operations in Java enables you to manage and organize files efficiently, ensuring data integrity and system reliability. By applying these skills, particularly in scenarios like the ConnectSphere platform, you can create, rename, and delete directories effectively while gracefully handling potential errors. These practices are vital for maintaining a scalable and dependable application. Playing video games is fun until you've cleared a tough level and want some snacks to celebrate. But before stepping away, you pause the game to make sure everything stays exactly as it is. Your character's position, inventory, and even the enemies. How does your game remember all this? In programming, this ability to save and restore the state of an object is known as serialization and deserialization. In this video, you'll explore how to use these concepts in Java to save the state of your objects and bring them back to life when you need them. Let's start with serialization. Serialization is a process of converting a Java object into a byte stream, which can be easily saved to a file, sent over a network, or stored in a database. The byte stream represents the object's state, making it possible to store it and reconstruct it later. Ready to see how this works in Java? Let's dive into some code. First, create a project named Adventure Game and define a simple player class with a few attributes. Right-click on the src folder, select New, click on Java Class, write the name of the class as Player, and press the Enter key. Define 3 attributes for the player. 1. Private string name. 2. Private int level. And 3. Private int score. You'll need a parameterized constructor to initialize these attributes and getters and setters. Right-click inside the class, select Generate, and choose Getter and Setter. In the new window, select all 3 attributes and OK. The getters and setters will now appear in the class. Now, let's override the toString method. Right-click in the class again, select Generate, and choose toString. Select all 3 attributes and OK. Your player class is now ready. Now the player class is ready. Let's prepare this class to be serialized. To make this class serializable, you need to do two things. First, implement the serializable interface in your player class. Second, define a serial version UID variable, which should be private, static, final, and of type long. The JVM verifies that the saved and loaded objects are compatible during serialization. If a serializable class doesn't declare a serial version UID, the JVM will generate one automatically at runtime. The serial version UID is used in Java's serialization mechanism to ensure that a deserialized object is compatible with the version of the class that was used to serialize it. Now, let's serialize an instance of the player class and save it to a file. For this, let's create a main class with the main method. First, create a player instance with the reference GameMaster13, passing the appropriate arguments to the constructor. Now, add a try-with-resources block and initialize a file output stream object. Pass in the name of the file as player.ser to the constructor. You can use any file extension here. Add the appropriate catch blocks to handle any potential exceptions. Inside the try block, initialize an object output stream object, passing the file output stream object to its constructor. Then, call the writeObject method on the object output stream instance, passing in the GameMaster13 instance as an argument. This will serialize the player instance and write its information to the player.ser file. Run the code and observe the output. It will create a new file called player.ser. Remember, the serialization process converts all attribute data into a byte stream and saves it to a file. However, attributes declared as static, like the serial version UID, are exempt from serialization. If any attribute contains sensitive data that you don't want to save, you can use the transient keyword to exclude it from serialization, like private transient string password. Next, we'll move on to deserialization, which is the reverse process of reading a byte stream and converting it back into an object. This is how you restore the state of your object, just like resuming that paused game. Now let's see how to read back the object you just saved. To deserialize an object in Java, the object input stream class is used to read the byte stream from the file and convert it back into a Java object. Create a new player instance and name it restoredPlayer. Initialize it with null. Add a try-with-resources block and initialize a file input stream instance, passing the name of the file where the player instance is saved as player.ser. Create an instance of the object input stream and pass in the file input stream object as an argument to its constructor. An object input stream deserializes primitive data and objects previously written using an object output stream. Now, call the readObject method on the object input stream instance. Add a catch block to catch the class-not-found exception. Cast the restored object into a player instance and store it back in the restored player object. Finally, you can print the restored player object to visualize that the state of the object has been restored. Let's run the code. You'll notice that the player object has been successfully serialized and deserialized, maintaining its state across different program executions. Although serialization and deserialization are powerful tools, there are a few things to watch out for. First, not all objects can be serialized. Transient fields, for instance, aren't saved as part of the object's state. Second, also be cautious with versioning. Changes to your class structure can break the deserialization process. always include a serial version UID in your class to avoid unexpected issues during deserialization. And third, remember, serialization should be used thoughtfully, as it can introduce security risks if not handled properly. In this video, you learned that serialization and deserialization are essential tools in Java that allow you to save and restore the state of your objects. Whether you're pausing a game or saving user preferences, understanding how to serialize and deserialize objects is a valuable skill. Now that you know how it works, why not try serializing and deserializing your objects? Happy coding! Congratulations! You are past the halfway mark of this course. There must have been times when you felt overwhelmed and unsure of what to do. But rest assured, you are closer than ever to becoming a junior software developer. Let's recap the concepts and techniques you've learned on file handling. Mastering file handling is essential for building robust and efficient applications as a beginner Java programmer. Whether you're storing game progress, managing user data, or organizing system logs, understanding how to interact with the file system is crucial. This module covered various operations you can perform on files and directories, from basic tasks like reading and writing to more advanced operations like serialization and directory management. Lesson 1 started with introducing files and directories. You began with the basics, learning what files are and why file handling matters. You now know that files act as containers for storing data on devices like hard drives and come in two main types: text files, which store human-readable data, and binary files, which store data in a computer-readable format. Java provides you with classes like file, file writer, and buffered reader to manage these files effectively. Next, you learned to perform standard file input and output, or I/O operations. These include creating, deleting, renaming, and copying files using the file class. This class gave you a simple API for basic tasks, making it easy to create a new file when a user uploads a document or rename a file as needed. You discovered that Java NIO, or New I/O, offers better performance and flexibility for more complex scenarios, especially in high concurrency environments where efficiency is key. Therefore, you learned how to use file writer and buffered writer to write and append data to text files. When logging user activity, you preserve existing logs while adding new entries by setting file writer in append mode. This allowed you to add new data to the end of a file without overwriting the existing content. However, for frequent write operations or large data volumes, you can use buffered writer to buffer data before writing it to the file, reducing the number of disk accesses and improving performance. This approach is particularly beneficial in scenarios where system responsiveness is critical, such as in a communication platform logging user interactions. Beyond individual file operations, you also master directory management, another critical aspect of file handling. You learned how to create, delete, and rename directories using the file class and Java NIO. For example, when a new user registers on a platform, you create a dedicated directory to store their data, ensuring it is organized and easily accessible. The file class offers straightforward basic methods for directory manipulation. However, Java NIO, with its path and files classes, provides a more robust solution for modern applications. NIO supports advanced operations like handling large directories, symbolic links, and atomic file operations, features that are essential for maintaining data integrity and system reliability in complex applications. In Lesson 2, you were introduced to streams through which data flows between your program and the file system, a vital part of file handling. Streams like file input stream and file output stream allow your program to read from or write to files. Then you learned the importance of managing streams properly to avoid resource leaks, which could cause your application to crash or behave unpredictably. By using Java's try with resources statement, you can automatically close the streams after use, whether an exception occurred or not. This feature ensured that resources were released promptly, preventing memory leaks and maintaining application stability. As you progressed through Lesson 3, you encountered more advanced topics like serialization and deserialization. You learned to serialize an object, converting it into a byte stream so you could save it to a file or transmit it over a network, and then deserialize it back into an object. This concept proved particularly useful when you needed to persist the state of an object, such as saving game progress. By serializing the game state, you saved it to a file and later deserialized it to restore the game exactly where you left off. Throughout the module, you followed best practices to ensure your file handling code was efficient and reliable. You consistently closed file streams to prevent resource leaks, used try with resources for cleaner code, and handled exceptions gracefully to allow your application to recover from errors without crashing. When dealing with concurrent access to files, such as when multiple processes write to the same file simultaneously, you implement file locking mechanisms. These mechanisms prevent data corruption by ensuring only one process can modify the file at a time. By mastering file handling in Java, you've laid a strong foundation for building reliable, efficient, and scalable applications. From reading and writing files to managing directories and serialization, you now have the knowledge and tools to handle files and directories effectively in Java. By following best practices and leveraging Java's advanced file handling APIs, you can ensure your applications are robust, efficient, and capable of managing data to support current and future needs. Happy coding!